And we can then ask it questions and we can interrogate it. And this is where we're interrogating it in real time. So the little coloured boxes are modules. And this is where we're arranging the modules around a containment unit and the main nuclear power plant itself. And this is where we're finding the optimised form for where the functions sit together. Now, this is an immensely complex three-dimensional puzzle that cannot be held in one person's head. So you need to use programs like this to optimise the design of an SMR. Now, to produce, levelised cost of energy, you need to optimise this, because we need to take up the smallest amount of space in the most efficient way with the best design. And this is a route that we're utilising to actually make sure that instead of designing the usual industry standard, which is a giant bungalow, because that's the way that engineers aren't trained in three-dimensional volumetric thinking. Architects are. I would say that, of course. But that's why most power stations end up being a giant bungalow, where everything is laid out horizontally. Because three-dimensional thinking is complicated, but it's more efficient. It's better from a functional point of view because you can get the function next to the function you need. It's better from a costing point of view because the unit is smaller. It's better from a design point of view because aesthetically the functionality is coming out in the architecture. It's actually starting to sing in its own way. And then piecing it all together, so you can see the shell roof over the top, which is using functionality actually. So as we bend and change and fluidly manipulate this thing, we can change with it. But then we've got all the functions below, and it's fluid systems, I think, we're slicing through there, the main system. And that doesn't show the actual modules inside there, but all the modules are designed by the different engineers. But as from the parametric point of view, we've measured them all together, and we can actually work out what the most optimized way of setting that three-dimensional puzzle out is. So this is a way, the paper that I wrote, or we wrote for this, was making the complex simple. It's an immensely complex thing that we're doing here. And there are methodologies that can be learned from outside of the industry that could inform the industry. And I think the industry is at a point at which it could learn from outside. And I think it's good for all industries to do that. Thank you.
So thank you very much, Andy Crabb, for the interesting presentation. For the next speaker, I would like to invite Professor Irfan Ali from ARC Clean Technology US. As the Chief Strategy Officer, will present on SMR deployment first of a kind, risk and risk mitigation strategies. Please.
Good afternoon. It's a pleasure to be here, and I appreciate your time. So, let's see. Green one, yes. Thank you. So, what I'd like to do in the next 30 minutes is share with you some perspective on one of the most critical risk elements that SMRs have to navigate, which is the risk of first of a kind. And my presentation is based on the experience that we've had as an SMR developer with our Fork project in Canada with New Brunswick Power. And to start off, I would like to give you an introduction to ARC. As a company. So ARC Clean Technology is a clean technology company headquartered in Washington, D.C. We are engaged in the design and development of a reactor called the ARC 100, which is based on SFR technology, sodium-cooled fast reactor technology. That is one of the options in the Gen 4 portfolio of next-generation nuclear technologies. So as some history and background in ARC, between 1963 and 1994, the U.S. government, through the Department of Energy, funded a program called the EBR-2 program. So this was a program that entailed the design, development, and operation of an SFR called the EBR-2, Experimental Breeder Reactor 2. The project was led by and managed by Argonne National Lab in conjunction with several partners. And over the course of 30 years, this project ran well, produced electricity without any major incidents, right? So it effectively proved the validity, the viability of SFR technology for future commercialization. When the program ended in 1994, GE Hitachi decided to commercialize that technology through a reactor called the PRISM. And the focus of the PRISM reactor was very specific. The use case they were looking at was used fuel disposition. ARC then decided to take that same technology base and commercialize it in the form of an ARC 100, initially for electricity generation, both in base load and for dispatch, but then subsequently for a combination of combined heat and power applications, right? And that's the process that we're engaged in today. The reactor that we're developing is called the ARC 100. It benefits from decades of investment from the U.S. government and other entities around the world. In this process, we have several key partners that we work with. GE Hitachi is a key commercial partner. They're also an investor in the company. Hatch is a leading Canadian engineering firm that's helping us in this process. New Brunswick Power is an early customer. We're fortunate to have them on our team. They have a target of 2030 to initiate operation of the first ARC 100 reactor to be built at the Point Lepreau nuclear site in New Brunswick. We're also a recipient of an ARDP award from the U.S. Department of Energy. It's the same program which includes companies like TerraPower and X-Energy. And then additionally, we work closely with a number of key partners: Argonne National Labs in the U.S., Idaho National Lab, Sandia National Lab, Canadian Nuclear Laboratories in Canada, and then United is an architect engineering firm that's helping us in this process. So just some high-level observations, right? So in comparison to large nuclear, SMR economics of manufacturing scale can offset the economies of production scale, right? So the reason that we built nuclear large and in the form factor that you find today was to derive economies of scale, right? But SMRs can offset the economies of production scale through economies of manufacturing scale. Because what we've seen with large projects is that scale has its own complexity and therefore cost, right? So in the US, we saw the Vogtle project, which ran over substantially in time and in cost. And a large part of that was the complexity that comes with scale. Potentially, with the simplified approach that SMRs can take, this offers a much larger global footprint for SMR deployment, right? So the large reactors that you find in the developed world are extremely difficult to envision in the developing markets. In a lot of cases, you don't have the grid infrastructure to accept 1,100 megawatts of incremental capacity. In markets like that, SMRs can be very effective as an option for nuclear energy, and therefore the potential footprint for SMRs globally could be much larger. At the same time, in entirely deregulated markets, what we call merchant markets in the US, SMRs can compete effectively against natural gas combined cycle and renewables, right? So SMRs have lower marginal costs than NGCC and yet higher capacity factor than renewable energy. And in the financial analysis that we do to compare the options, our view is the total system cost needs to be included, right? And yes, to some extent, it's reflected in the form of a lower capacity factor for renewable energy, but nonetheless, a lot of the other components of total system cost are not. And in all the financial modeling that we do in support of our product development, we ensure that we include the full system cost that goes into supporting renewables. At the same time, higher outlet temperatures with some of the advanced technologies can offer incremental revenue. So in our case, with the ARC 100, our outlet temperature is 510 degrees C, right, which is substantially higher than the 350, 355 that you find in existing light water reactors. So therefore, now you have the option of addressing a number of other applications and use cases that you could not before. So bottom line is to enhance the economic competitiveness of SMRs against other options. Our view is the dual focus has to be on cost reduction and incremental revenue. But to realize the full potential of SMR technology, several key challenges have to be addressed, right? And the key distinct challenge that I'm focusing on today, that is by far the most critical, is that of the development and construction of folk projects, first of a kind, right? So This is not unique to nuclear. Fork risks are not unique to nuclear or other technologies, but they're specifically distinct for fork projects for SMRs and nuclear. Specific risk elements: technology risk, the maturity and development of the underlying technology is key. The core design that a lot of new reactor technologies use. So the focus is on using HALEU, high assay, low enriched uranium. So this is under 20%, could be as high as 19%. This is not what the nuclear industry is used to, right? So therefore, this presents a technology risk element that has to be addressed. Options for heat transfer. A lot of the new technologies propose different methods for transferring heat, and effective as those options are, there are risks associated with the new options. Then lastly, in the technology risk, transition from technology to product. So even in instances where the technologies might be high on the TRL level, still the process of taking technology to commercial product is complex, right? And it's particularly complex in nuclear because of the number, just the sheer number of components and systems involved in a nuclear power plant. The next risk is financial, right? How do you get nuclear SMR fork projects financed, right? So this is a key challenge that all of us developers have to navigate. And there are two components to that risk. The first, of course, is how do you get the initial funding? And the second one is how do you do effective project and financial management so that you can minimize cost overruns that are inevitable. Cost overruns will happen. How do you minimize them? That's another risk component that has to be addressed. For regulatory oversight, this is a singular factor that differentiates nuclear projects, right? It's not that nuclear is the only industry that has regulatory oversight. It's that the nuclear industry has regulatory oversight that's by far the most stringent for all the obvious reasons, right? But nonetheless, this implies a particularly high hurdle for the nuclear industry, for the SMR industry, to facilitate the deployment of new nuclear. For the regulators, there's a steep learning curve in transition to new technologies, right? So some of the regulators have stepped up to this challenge better than others, but nonetheless, all the regulators are used to regulating older technologies, right? Whether it's light water reactors or it's CANDU reactors. The transition now, all of a sudden, to new reactors like SFR and HTGRs and molten salt reactors presents a steep learning curve for the regulators, and yet that is something that we have to navigate as developers. This takes a significant commitment in time and resources and therefore cost, right? So by far, one of the largest elements of cost in developing fork projects is regulatory compliance, right? So getting the initial design licensed and then the associated oversight that comes in building new projects. Then lastly, the strategic risk is intangible, but is often the most crucial, right? So this is where there has to be strategic alignment between all principles. And I'll talk about this some more in the subsequent slides, but the fact is that a single unit fork plant will not be economically viable, right? Just the numbers, that's how they add up. And therefore, there has to be a larger strategic vision that is defined and shared by all the principles involved in the project such that the project can be successful. So in terms of mitigation of the risks that I have shared with you in the previous slide, the technology risk could be mitigated through simplification, right? So it's always tempting to have the product do more, right? I mean, that's what us engineers specialize in. We want our product to do more features. However, to be successful with the fork project, simplification is the key, right? So define the project to the minimum required features and then focus on developing it well. Plus the effective management of the product life cycle, right? So this is an important component that I'll address in the slide. An early simplified technical definition of the project should help. In selecting suppliers, cost should not be a prime consideration. There will be ample time, ample opportunity to have supply chain diversification in the subsequent years. But for the fork project, the focus should not be on cost. It should be on selecting suppliers that have the track record and the technical ability to deliver, even if the components are more expensive at that point. An empowered product management function could make a crucial difference, right? So product management, I come from the telecom networking software development environment. And across multiple industries, an effective product management function can make a big difference. Surprisingly, that is not as extensively used in nuclear. I think that could make a difference in managing the product lifecycle. For financial risks, public financing options could be significant for project success. In the U.S., we have that in the form of direct assistance through the ARDP program, right? So we are a recipient of that help. X-Energy, TerraPower, General Atomics, we are all recipients of that help. But additionally, indirect help, government help in the form of loan guarantees, which lowers your cost of capital, production tax credits, investment tax credits are all options that should help. And then once that funding is raised, effective financial management to minimize cost overruns is very important, right? So for milestone-based financing, which is often the case, you don't get all the money up front, you get money based on milestones you meet. The risk mitigation has to be upstream, as in the risk has to be addressed long before it happens, right? So root cause has to be analyzed upstream. And then management of financial expectations, which is single unit versus fleet deployment, is very important. As I indicated, a single unit fork is not going to be economically viable. And yet, how do you transition from a single unit to a fleet? That's an important question. On the regulatory side, early engagement with the regulator could make a difference, right? So in some instances, like we work with the CNSC has a very effective formal approach to doing this. It's called the vendor design review process. In the US, we work with the NRC in what's called the pre-application engagement process, where we meet regularly with the NRC, offer them white papers, technical reports for feedback and review, and the feedback is very useful. And yet this feedback, for its full value, has to be integrated fully into the design and development of the reactor system, right? So that's an important part. And then organizational stability could be a key critical success factor. The regulatory process for nuclear and SMRs and folk is long and tough. And of course, every organization is going to have some churn, but in this case, organizational stability is a very, very important requirement. Then lastly, the strategic rationale for the folk project should be clearly articulated. There has to be a common understanding between all the principals for how you go from folk to NOC, and the enduring commitment of the major stakeholders could make the difference between success and failure. Of course, changes happen. But if you have too much change, too much churn in the original consortium that's initiating the folk project, then it's often difficult to recover from a change like that. So in conclusion, the desired zero-carbon environment of the future is not possible without nuclear energy, right? I mean, I think that's becoming an accepted fact, not just within the nuclear industry, but across the entire economy. However, a critical hurdle is the transition from folk to NOC, right? For nuclear, for SMRs, a critical hurdle is the transition from folk to NOC. SMR folk projects have a unique risk profile. Specifically, that includes technical, financial, regulatory, and strategic risks. The key resulting challenge is that an economic model is an economic model that's biased against single unit deployments. Just very difficult to make those economically viable. In the spectrum of risk that I've discussed with you, strategic risk could be the most critical. And yet what we have to recognize is that every successful SMR folk project improves the credibility of the entire nuclear industry. That helps all of us, so we're all very supportive of every single success that happens in this industry. Thank you.
Thank you very much, Irfan Ali, for the insightful presentation. So I will invite our next speakers. It will be Marco Caramello from Ansaldo Nuclear SPA Italy. Will present on Italy's journey into SMR, research safety assessment, testing, and future prospects.
Thank you, and good afternoon to everybody. So today, my mission is to bring you back through history, talking about the activities which were performed in Italy under the SMR framework. So what I'm going to do is going to start from legacy reactor projects, because SMRs in Italy were developed also very fast. And coming to also the first and the reactors which are being developed today, leveraging on advanced technologies. I will also touch the industrial fabric, so the current supply chain, the Italian supply chain, and what we are doing in this new nuclear renaissance. And I will complete with a few examples related to the research and development, particularly on thermal hydraulics, on the licensing and the future prospects. So, for those of you who are at least my age, will remember that we were talking about SMR 15 years ago. In that occasion, the SMR product was not able to reach the market because of a completely different economic environment. A similar approach was also applied in Italy back in the days between the 1986 to the 90s. The reason in that case for us was to find or identify technical solutions which were smaller, simpler, and could leverage advanced safety features such as passive modes in order to protect from anticipated accidents. These were the driving elements which in the past provided a few examples of reactor concepts which never saw the light. Nevertheless, allowed some technological spillovers in other sectors and overall protected the overall knowledge of the technology. Nowadays, in Italy, one of the most prominent reactor concepts that is currently being developed is the lead-fast reactor, the LFR, which provides for many ambitions, such as the closure of the fuel cycle and also design simplification. And of course, there are many challenges which are being addressed by research. One of the notable examples is Alfred, which is currently being selected within the Industrial Alliance as project work. And this Alfred aims to be a European demonstrator for the follow-on reactor class. Coming back to industry, so the news in the last year regarding the possibility to resume a nuclear program in Italy have raised interest in all the industry, and many projects have been launched in order to map the capabilities and also the capacity. One of the projects which I want to mention is the one promoted by the Polytechnic of Milan, which provided for a case study in relation to the reactor pressure vessels of a prototypical SMR to understand how the Italian industry could support the construction, and the results show that up to at stage the Italian industry could support with the construction of 8 reactor pressure vessels per year. If you have a further question about this, I invite you to speak with Professor Ricotti near me. Now, together with industry, research is an active animal in Italy, which has been developed since the 60s and onwards. Historically, we have been a place where many integral effect test facilities have been designed, constructed and operated to support the licensing of several reactors which are currently being built today. The knowledge management and the capability to maintain this capacity was also renewed in the last few years, as many vendors have chosen several industrial sites in Italy for the design and the operation of mock-ups and large-scale experiments for proving the new innovative concepts. Here there is an example of the steam generator validation for no scale provided in SIET. Together with large-scale experiments, also separate effect test facilities have been built and operated in the past. Here I want to mention 2 of the most prominent examples. One is named Sirio, which I where I spent 3 years of my PhD on, and the aim of this facility is to test and validate the safety feature of decay heat removal for LFRs, having the capacity to passively modulate the power removed. Another notable example, which was touched by one of the presenters before me, is the SMR facility, which was an experimental loop aimed at demonstrating the capability to use innovative technologies, in this case a microchannel heat exchangers, inside a passive safety system for removing the decay heat, and also all the related complexities with respect to the performance, the stability, and the overall behavior in single-phase and two-phase flow. Together with the experiments and the post-test analysis passes through the benchmark and validation of computational codes, which have been used in the past by research centers and the Italian academia in several international groups and European projects. The benchmarking has been performed both on system codes, so RELAP 5, Qatar, Trace, as well as computational fluid dynamic tools, and the analysis and validation of the coupling between those two type of models. Finally, even though Italy is not a country where new plants have been built in the present and in the past, there has been a large work on, especially concerning the safety and licensing. In particular, several industries have been actively involved in drafting and developing documentation for some of the newest reactors being built now, and the main focus and the main capacity which was retained in the last 10 years was the one related to the safety assessment, to the thermal hydraulic validation, and also with the development of advanced methods such as the BEPU, which is a well-known method for understanding and assessing the uncertainties related to code analysis and benchmarking. So, to conclude, in this short presentation, my aim is to pass a few messages, which are that in the last few years, Italy has been discussing again the possibility to include nuclear power within its energy mix, and this is driven by several factors, including the large amount of expected power increase due to the natural consumption and also the electrification. Due to, let's say, the capability of the industry, of the research and the academia to maintain knowledge and competence, all of these three aspects of the Italian ecosystem proved to be resilient in order to maintain key skills, capabilities and capacity to cover these needs, and all of them shall increase for sure the capacity to sustain a nuclear power program. Overall, the Italian country is looking in the short term in developing potentially SMRs based on light water reactor technology, and on the medium term to explore advanced modular reactors based on liquid lead or associated heavy liquid metal. Thank you very much, and open to questions.
Thank you very much, Marco, for the presentation. And then I will invite our last speaker for this session, Ron Feibist from General Atomic of US, will present about GAEMS fast modular reactor. Please.
Good afternoon. Many people said good morning yesterday at this time, so it's good afternoon, depending on where you are in the world, I guess. Thank you for the opportunity to present, and I actually stood up after Irfan finished because he set the stage so well for me, and then, you know, Marco, of course, you did a great job, but, you know, you're in between the setup and this. But so we both are supported, both Irfan's company and my company are supported by the Department of Energy in a public-private partnership to develop the fast modular reactor. Oh, I have the slides here. And this is the agenda for today. I'm going to give you a brief overview of General Atomics and our fission work since the 50s. We've been around for quite a while. We do many other things. It's a big company, wholly owned by privately in the US. So we develop other advanced technologies, not just nuclear. I'm going to talk about the key design features of our reactor, some market considerations that we are following. I'm going to talk about a special spearheaded effort that we had with other industries in the US. It's called the Accelerated Fuel Qualification to enable much faster qualification of advanced fuels, which I think is important for advanced reactors, especially Gen 4. And then I'll talk about a little bit of the regulatory engagement. I'm going to stay away from costs because I personally do not believe in LCOEs, and we can have a long discussions about that afterwards. So General Atomics, you probably are familiar with our trigger reactors. We have built 66 of them around the world. The world's probably safest reactors, pool type, with UZRH fuel that is being manufactured in France, just outside Lyon. We just reestablished manufacturing with Framatome in a 50-50% cost share there partnership. We make fuel right now. It's a HALEU, high assay, low enriched uranium, 90.75% enrichment as far as I remember. And it goes into research reactors in the US and around the world. These reactors are in the backyard of universities, making medical isotopes and really training the generations of the future. And we see renewed interest in trigger and in research reactors in general. It's a wonderful tool to advance, especially in the developing world, nuclear technologies and education of nuclear. And by the way, make some medical isotopes in the process. So we built that in the 1950s as a first of a kind at GA in San Diego. You won't find too many reactors being built in California these days, but we're encouraged by the fact that Diablo Canyon was extended in terms of life extension recently. So things may be changing for much, much better in the United States, and I think they already are. But in some states that have not, I would say, were very friendly to reestablish nuclear as an energy source. We are known for our gas-cooled reactors, the only two commercial high-temperature gas-cooled reactors in the US, Peach Bottom and Fort St. Vrain. We made lots of TRISO fuel for those reactors. We made it in La Jolla, San Diego, in Torrey Pines. Golf course and TRISO fuel manufacturing. That's a wonderful image. It doesn't exist anymore. We believe that TRISO fuel presented some economic issues if we want to use it in the line of future reactors. As some of you know, or many of you know, energy density of TRISO-fueled reactors is not very high. It presents a challenge of economy of scale when you try to scale up TRISO-fueled reactors. So we decided to go in a different path and use usual cladded fuel pellets that you can see a picture of in the bottom. We make prototype fuel. We make radiological monitoring systems for existing fleet and the future fleet. And we also are supporting our space industry or space government agencies in developing space nuclear propulsion and power options for the future. So that's an emerging area for us. We have lots of knowledge of how to do those things in extreme conditions. So we make what's called the SIGA, silicon carbide technologies. It's cladding that can withstand very high temperatures. For our reactor, you're going to see is 800 degrees C operating temperature. And this material, as a ceramic matrix composite, CMC, offers us an opportunity to really develop very high temperature reactors, even beyond that temperature. It's just practical limitations of the reactor design. And we know how to make those cladding materials very well. We're leveraging also the accident tolerant fuel program in the US, the Department of Energy program as well, that's cost share with us as well, to develop the cladding of the future that would prevent, zirconium type cladding where you have those hydrogen, God forbid, in abnormal conditions or accidents, hydrogen explosions and things such as that. So we believe in materials. As you can see from all of this, I think most of this slide shows advanced materials, and that's what makes us unique. So the fast modular reactor is a 44 megawatt electric, 100 megawatt thermal reactor. It uses a Brayton cycle. I'm going to show that. Direct cycle. It offers passive safety, flexible power, up and down, very load following, high burn up, and cycle efficiency. We really want to take advantage of a fast spectrum neutron reactor that burns very long-lived actinides and can close the fuel cycle. At the same time, can offer you a lot of energy that can be converted directly through this gas cycle to a Brayton cycle. So the efficiency will be very high. So safety, economics, less waste, and proliferation resistance in terms of making sure we use the latest recycling options if recycling is economical. So we believe that closing the fuel cycle is an option. It's not a necessity, but we think that some countries see it as a vital option for them, like France, for example. But in the US, obviously, it's still being assessed. I think there has been a change in why we're going nuclear. You heard a lot about it, but I would sum it like this. Once we said, let's go 100% renewable. Then we said, let's do 100% clean energy. And let's go, carbon neutral by 2030. And then let's triple net zero production by 2050, especially of nuclear. This was an evolution of thinking, and I think we're in a very interesting time now when we really value net zero by 2050. So I think it's very good for all of us. The market that we are pursuing, this reactor is very scalable. I'm not going to get into how. I think you can imagine fast neutron cores lend themselves to scalability rather readily. So our target market can be one of many things, and we do appreciate cogeneration as a viable option. We see industrial heat as picking up steam, no pun intended. And actually, I just thought about that. That's pretty good. But we see also the future of EVs. If they're really going to pick up, you need to produce a lot of electrons. Data centers, obviously a lot of people are talking about AI. It's a booming industry. It's going to be just exponentially growing. And it's not a joke anymore. They need the power. So we see a lot of opportunity for us in that regime. The parameters of the reactor, like I said, it has a 42% thermal efficiency, net thermal efficiency, 44 to 45 gross, 800 degrees C. Refueling, you do not touch our reactor for at least 15 years. Some of you may remember the EM squared concept that we still develop, but it's a longer-term concept, 265 megawatts, 4 modules for a gigawatt baseload plant. That had a 30-year life cycle. So you only replace about a third of the fuel and then reshuffle after 15 years, and that's close to 100% capacity factor. So it would be longer. So fuel life is 45 years, basically. Fuel burnup is very high. It's more than twice than the BWR, for example. And we are at the 7 bar pressure, so it's also a little bit less than BWR. And we know how to manage helium. We have done it before. Reduction in high-level waste, obviously, because of the fast spectrum. 20% power per minute ramping up and down. That's incredible if you think about it. We can compete with gas turbines quite easily. And of course, system temperature during emergency cooling is much less than 1800 degrees C. Hopefully, we not get to emergency cooling, but if we need to get there, our cladding, there are 3 barriers. I can get into the 3 barriers, defense in depth, physical barriers, not to speak of the actual design of the reactor or the neutronics that will allow us to withstand severe accidents. And it's scalable, as I said. So this is a sum up of everything that I just said. Slight flexibility for us is key. The dry cooling of this reactor, it's dry cooled. There's an option to wet cool as well. But if you think about it, water is not an easy situation around the world, especially with climate change being a factor as we go down the road here. We want to be flexible and not depend on water for cooling. We have some makeup water for obviously the systems that we operate, for the cooling with the obviously dry cooling towers, but we can rely on air to do our cooling. This is what I talked about. We have a white paper on atoms, the Nuclear Regulatory Commission. You can search for accelerated fuel qualification. It's an 18 or 19-page white paper that I led the authorship on. And it basically brings down qualification using modeling and simulation together with experimental data to bring down the number of years. You know, to qualify new fuel, the nuclear engineers of us know that you need to do a lot of integral tests. And that takes time. We don't have too many radiation opportunities in reactors these days. To alleviate the issue, I think the hybridization of modeling and simulation and experimental data without compromising safety case is the way to go. And we are working very hard on that to make that happen with the NRC engagement. What's something that Irfan said that I totally agree, engage the regulator early and often. And we are doing it with, throughout the last 3 years of conceptual design. We have submitted several documents to the NRC, gotten feedback. We have a large team. I haven't even talked about our team. Framatome is on our team, for example, as a partner. We have national labs, universities. It's a big, it's a big team that enables GA to get get the dream into reality. And it's not a dream anymore. It's actually happening. Our deployment target, as I said, is in the 2030s. And we are not in a hurry per se. I think things have to line up in terms of financing and everything else that people have talked about. We are patient. We call it strategic patience. And there's going to be a lot of opportunity for many of us. And I think that people, the companies that stay around will benefit from a market that's going to open up quite a bit in the 2030s into the 2040s with lots of retirements coming up of all kinds of plants. And with that, I'll end up and have 1:50, right? Thank you very much for your attention.
Thank you to all the presenters, the authors, but the work is not finished, so I will ask you to join us on the stage, because we will start the question and answer session. And while the authors will come to the stage, please raise your hand and start thinking and asking questions to the panelists. Yes, you should have the microphone to directly answer.
So the two chair will be here.
Oh. Please.
Hermes Llanes from Colombia. We know that it's a complete challenge to get the first-of-a-kind prize, but what say the authors about an N-of-a-kind? Do you have some approach to that prize? Talking about CapEx.
To all the speakers, or?
Speakers or all?
Yeah,
okay.
all. Thank you.
Okay.
Maybe from
Who wants?
Willem? You want? You have? Yeah.
Thank you. Can you hear me okay? Yes. Yeah. So I think, and that's an important question and an important consideration is how do you go from fork to NOAK, and in that transition, how do you bring the cost down? For the capital cost, our estimate that we use in our models is from fork to noke, a cost reduction of about 40%. Now, that transition from fork to noke can vary by vendor, and it can vary by technology, but in our case, roughly noke equals fork plus 8 or fork plus 10. But in that transition, we hope to reduce the capital cost by 40%. Secondly, the target that we are using in all our financial modeling is that at noke or LCOE, and this is for electricity generation obviously, the target is to stay under 5 cents per kilowatt hour, right? So that's a target. And so why is that important? Because we use that target in all our design considerations, all our analysis, because we feel that globally, if we can stay below 5 cents per kilowatt hour for LCOE, then we will be competitive against any other option.
So yeah, maybe I can add, Irfan, thanks for the answer. I think you heard targets, and I think that's what we have. We have targets to work towards, and there's quite a few reports out there, even from the Department of Energy. Recently, they released the liftoff report that provides ranges of what makes sense for nuclear to compete in the open market. So we are all working towards those targets, and I think capital cost and operating costs, those are the components that we should really look at. We have other issues to worry about, right? We need a fuel supply, reliable fuel supply of high assay, low enriched uranium. A lot of our concepts that are advanced will rely on that. That has a cost eventually. So I think there are a lot of factors in it, so we can work towards a target, and that's why LCOE is such an elusive number for us, and it's really difficult to predict 10 years out what that number may be at that particular moment in time, especially for us, right? That's the runway that we have. So just food for thought in terms of targets.
Yeah, Marco, please, you have a comment?
If I can add one thing is that the topic, of course, is to deliver a project on budget and on time. And this is done in a collective fashion through all the supply chain, meaning that to build large or small components in series means learning how to do it and deliver it in a practical and let's say allowable rate, so that things can be forecasted and planned in advance. This is one of the key aspects that will need to be delivered in the SMR model in order to provide value.
Thank you. Andy, you have comment? Andy, yeah, please.
I mean, from Rolls-Royce's point of view, they're scheduling it out across a sort of 8 to 10 year period. So it's very much a reality. Also, at the same time, we're engaging with the suppliers throughout the procedure at this point, so that we're actually getting that information directly into the design itself, so that there should be no surprises within the whole thing. The Rolls-Royce SMR also works from inside a site factory. So the intention is to actually build it within a site factory so that we can actually determine the unknowns to a greater extent than you normally would, which is a unique point within the SMR.
Please, Billy, you have a comment?
Yeah, so, well, I guess if I may take another hat on me, because I'm also working as part in the European SMR Industrial Alliance, like Professor Ricotti here also. And basically one of these things is that it has been, like, of course, understood that the first one will require like much more effort than the end of a kind. So there needs to be like support, either backing from somebody who has the like deep pockets, or like national or international support. Like in EU, now we have the Industrial Alliance to support the first of a kinds. So with the kind of like idea that the next end of a kind will then come commercially. In USA, there are different kind of like supports for the first one. So of course it needs to then with this kind of like public support we also need to tend to see that there is going to be some public good, more work competencies and so on. But this is kind of I mean, everybody understands that the first of a kind is much more expensive. How to actually accomplish that? That's a big question now.
I hope that the answer was successful. Please, we have a question.
Yes, hi, Andy Patterson with Allied Nuclear Partners. I continue to be amazed that small modular reactor companies try to pursue 5 cents a kilowatt hour when there are plenty of markets, remote mining, high critical installations, mass transit, and now data centers that'll pay 10, 12 cents. Mining will pay 30, 40 cents a kilowatt hour. There's plenty of market to sell there. Why are you trying to compete with wind at night?
So, I totally agree, Andy. And compete with solar during the day, I don't know. I mean, you need large batteries to enable renewables anyways. But I totally agree that, we have to be realistic about cost. And there are opportunities out there, as you say. I mean, electricity is going to be expensive to some applications, and they're willing to pay the premium because they need it. The same with the heat. And with decarbonization around the world, as we heard throughout this conference, there's going to be lots of opportunities in the future, and we're going to be sought after. Nuclear is going to be sought after at the various size ranges. And so we have a lot to hope for. Thanks.
Great. So, Andy, two-part answer. First, yes, I'll gladly take 10 cents, 15 cents, 20 cents. I won't object to that. But secondly, we are designing a product for the global market, right? So, and although the initial beachhead market is North America, as you know, we have a project in Canada. That's where our Folk project is with NB Power. And then we're obviously, through the ARDP program, focused on the U.S. as building our Folk in the U.S. No later than 2035. At the same time, and as you know, the ARDP program funded by the US DOE, a big part of that is the export market, right? So we're designing a product for the global market, although the beachhead is in North America. And, we'll gladly take a higher LCOE if we can, but at the same time, we are imposing on ourselves a discipline to build a product that'll be competitive in the long term for the entire world. Right, so that's the reason for that analysis.
I think the reality is that what you just said about the long term is the thing that we need to concentrate on. We have a fresh horizon here, and we need to be careful that we don't rush at this fresh horizon. What we need to do is do what we do well and make sure that the public are with us in what we're doing, and we work to the longer term in this equation.
Please.
Dan Șerbanescu, Technical Director, RoPower SA, Romania. So we are actually some of the few who applied for a site license for SMR in Deutsche. What I wanted to share with you and to ask as a question is the fact that when we did that for a brownfield, which was a former coal-fired plant. We did that in order to restart economical activity in a certain area, which was highly damaged. We did that having already a photovoltaic plant of 70 megawatts and a battery plant, and planning to build a hydrogen production plant. So that the plan now is, on medium and long term, to have a hybrid energy platform, not a nuclear power plant only. For that hybrid energy platform, we are organizing now to get an industrial regional platform which would need various types of energies we can provide from this platform. So my question was, first one was, don't you think that that would be more fair for SMRs to approach to? And the second part is, in our investigations, we came to the conclusion, based on Energy Observer Agency in the United States, that maybe LCOE is not fair to SMRs. Maybe we'll also use a combination of LCOE and LACE. And that, if we do that, then we are quite close to the situation in which the renewables were 10 years ago. Thank you.
If I could address, yeah, no, I think that's a very good point. And what I'd like to share with you is that in Canada, we have a second project at Port Baldoon, which is for an industrial site. And the focus there is on combined heat and power applications, right? And one specific area of interest is green hydrogen production, right, for either local use on site or conversion to ammonia for transport to Europe, right? Now, again, the economics of that last option need to be analyzed. But nonetheless, as I indicated, in our case, our initial focus was on electricity generation, both as base load and dispatch. And that's where the LCOE number is relevant. But then beyond that, we are looking at combined heat and power applications. And plus, the project that I mentioned at Point Lepreau with NB Power, we are also looking at isotope production in the same unit, right? So given our system, we can do isotope production without any disruption to the rest of the reactor operation, right? So you can insert material, extract it from the reactor, even as the reactor is running at steady state, and that's an incremental source of revenue, right? So that's where our focus beyond the initial deployment for energy is on combined heat and power applications. And it's a small reactor, 100 megawatts electrical. It's a small footprint, 13 acres, about 13 acres total, which means that proximity to the user is much easier, right? And especially for heat applications, if you're looking particularly at district heating type applications, distance is an issue. But with a reactor like ours, it can sit very close to the end customer and very safely, right? So CHP is a key area of focus that we're spending a lot of time on.
If I can add just one point is that for sure, given the size, now the possibilities of involving an SMR within an economic model involving baseload production, on-demand production, process heat, hydrogen. There are many examples which can be leveraged. One aspect which sometimes is never taken correctly into account in all the economic models is the term of externalities, which in case of nuclear power are largely positive and reducing the overall effective price. This number, which is not a parameter that you find on the book, but comes after a fruitful analysis of different scenarios, let's say it's something that should be accounted within these development models and maybe better or in a different way, so that we can also give a number to how much value is in energy security, how much value is in clean energy, and so on. And this could be beneficial in the economic models.
Okay, so my question is directed at I'm here. My question is directed at Mr. Crabb. So I liked your application of parametric thinking to making the complex simple. I would like to ask how different, or is parametric thinking fundamentally different from systems thinking? And if it is, would you find any complementarities in the applications? Thank you.
I'm not particularly au fait with systems thinking, but in principle, parametric thinking represents very much how our brains operate. What it tends to do is you have to set out the question at hand and work to that question. Now, the difference with parametric thinking to most thinking is you have to question what the question is, because frequently we forget to do that. We rush into design and we forget to analyze what we're trying to answer. With parametric thinking, you have to very rigorously set the question out. Once you've set the question out, then you can actually add the metadata into the system to start answering that question. But you have to define the question at the front hand. That's something that is frequently missed in nearly all aspects of life. And it's a rigor that you have to apply. Now, it's something that we tend to do in our brains. We sort of get to the answer very, very quickly in our heads. We then spend the next 4 years reproving where we got to within a split second. That's where our brain has automatically looked at the question at hand, worked through an awful lot of things very quickly, and then we have to reanalyze it to reprove to ourselves why we're going down that route. Now, it's not always right, but it is all about being at one with the question itself and setting that out. Now, I'm sure there are parallels and there are probably overlaps, so it is probably worth something to look into. So I agree.
We have a couple of questions there. First, please.
Yeah, Dave Greiner from Hitachi Energy. Considering the supply chain question that we've all talked about many times and the economics of making that, many of the countries or customers where I go to, they all want to have an in-country manufacture and assembly of the SMR. So how, as the vendors, will you address that challenge of proving out the supply chain if we have to rebuild it multiple times in every country? Thank you.
The question refers to oral speakers? Okay, please. Who first? Oh,
I think that's a very important question. And that's one of the questions that we deal with as we look at the transition from fork to no, right? But for the earlier projects, fork plus 1, fork plus 2, the emphasis has to be on delivery on time and under budget, right? So the fact is that over the long term, we accept the fact, we welcome the fact that our supply chain is going to be global. But how do we get there, right? So initially, given that some of the technology components and systems are new, we go where we find them, right? So in my reactor with the ARC 100, we use EM pumps. There's not a whole lot of vendors that can make EM pumps to our spec. So for the earlier projects, we have to buy EM pumps from people that can meet our specs and our time requirements, right? So that gets set by default. Now, over time, one of the elements that reduces the cost from fork to no is supply chain diversification, is where I can have competitive offerings or competitive bids for every single component in my supply chain. I can drive the cost down. But to get there, I have to then rely on wide availability of that particular technology. So I think for the initial projects, the supply chain is going to get defined by default. And even though there is a lot of interest in markets for local content, the markets still understand that in order to meet the time and cost requirements of the projects, that will have to wait. Right now, this doesn't apply to all of it. There are some things that can be done locally and done very well locally, and then that can be done cheaper, and we will absolutely go with that, right? So as a part of the consortium that's making these projects happen, we have a natural incentive to keep the cost down as low as possible, and yet at the same time, make sure that the project gets delivered on time, right? So this is going to be defined by default, and as this technology becomes more pervasive throughout the world, we will find the supply chains also becoming global over time.
So I would like to add, I guess some of us have the advantage of having in-house capabilities. So GA has a lot of manufacturing capabilities in-house. We're going to leverage a lot of that. We have a lot of space for nuclear production. We have a big manufacturing facility in Mississippi, for example, that builds a lot of our advanced systems beyond nuclear. We have a lot of in-house capabilities. I think one of the most things that worries me is the fuel supply chain. I think the U.S. Department of Energy, and in the U.S. we're now taking it very seriously. I think we're all facing similar supply chain challenges. And if we're going on a national level and global level in terms of nations tackling what are the key supply chain, critical supply chain materials and components, if we tackle it together, I think it will alleviate a lot of the pressure in the future. But selfishly, some companies like ours that are a little bit bigger, more established, I think we can guarantee more, I would say, high probability of manufacturing success if you have in-house capabilities to do it.
Okay, we have time for last question, please.
Irfan Ali from ARC. gave a very nice description of risks and mitigation for first of a kind. I do agree with all the risks, but when it comes to mitigation, I believe that there is a big opportunity in using new technologies like advanced manufacturing and artificial intelligence to help reduce the cost. Because my view is that if you keep on doing design, engineering, and construction the way that you had always done, that you will never reduce the cost. And I am surprised that this big conference with over 200 papers, there's only about 2 that talk about this big opportunity of using digital technologies to reduce the deployment cost of SMRs. And I was just wondering what the panel's view is on use of these new technologies.
Nawal, thank you for that question. I think that's a very important question. And of course, my thanks and compliments to you for highlighting this important point. And I know you were presenting a paper, I think tomorrow, on the use of AI. What I didn't get a chance to talk to is about how we are, in fact, looking at AI, ML for a number of things within our design process. So, for instance, one of the elements that reduces cost is the cost of operation, right? So we are moving to a model of fleet management where from a centralized point, a centralized operating room, you should be able to manage multiple reactors. A big part of that, though, is predictive analytics, right? So when it comes to I&C, we are looking at using a hybrid of digital analog sensors as appropriate, but then at the same time, making use of the generated data and plus synthetic data, plus historical data to do predictive analytics that should over time help us reduce our operational costs significantly, right? So this is a big difference from the environment that you find today where you've got dedicated teams per site, per reactor, because that's how we've done it. But I think as we get increasingly better at using predictive analytics through the use of AI, ML, we feel that this will be a part of how we bring the cost down and make SMRs more cost effective.
So I will also add, in our case, I showed the accelerated fuel qualification where we do those elements of AI and ML in getting the data to generate the features that we need in combination with experiments. So we're actively doing it for qualifying new materials, but we also have digital twin efforts for our materials, which is actually projects that are being co-sponsored between us and the Department of Energy that see the advantage in doing digital computing in order to do predictive computing for the different advanced materials that we're using and optimizing them for the performance. So I think it's a very valid point, and we're going to see only increase in doing that, which will be optimizing costs and also reducing the overall cost of their offering.
If I could real quick, Nawal, your paper is when, tomorrow or Thursday?
It's Thursday.
Thursday, my apologies. So I would encourage all of you to take the time to attend Nawal's paper. He's talking about how you use AI, ML to be more effective in delivering advanced solutions with nuclear energy. I look forward to it, Nawal.
Andy, please.
One thing. Which one? Okay. One thing I'd say is that when I first came to this sector, from a different perspective, it looked very similar to what it's always looked. 75 years ago we designed these things, and 75 years later they look pretty similar. I think that we could take some criticism as an industry that I don't think we do use the digital tools that we have at hand, and we should be using them more. I honestly think that we should learn from other industries and we should apply those techniques to this industry. This needs to be an industry that modernizes itself, and it still looks like an industry from 75 years ago. Now, I'm sure that the technology, as I said, I'm not a nuclear engineer, and I'm very much hoping that all the stuff inside is very clever and we're doing very clever things. But the reality is, to the outside world, and this has to be sold to the outside world, the industry still looks like it's always looked. And I agree with the questioner that we should be looking at these digital techniques, utilizing them, grabbing hold of them at a huge opportunity that we have open to all of us here, and actually using it with some pride in what we do, to revolutionize an industry. This is a huge opportunity, and I don't see the impetus in the industry to actually grab hold of it as much as we could.
30 seconds, please.
Yes, okay. Since we have been working to support the regulator on the other side, so just a small comment on, we did actually use some machine learning trying to figure out, some of the safety relevant cases. And I mean, for operations and for design, I think the machine learning is has very high potential. But then on the other hand, we will, as a nuclear field, we will of course need to understand its limitations, because if we are looking at very rare cases, and this is something where the machine learning is in a rather dire straits at this moment, because it relies on data, and if we don't have too much data, then it's kind of something that's not going to happen. And of course, with the vendors, I would very much like them to contribute the global resources of data for their new novel solutions, new novel materials, because this is actually something that we are lacking at the moment quite much when we are hearing about these very fine new solutions.
Thank you. We are going to the conclusion. First of all, Ms. Trianti and myself, we were very glad to co-chair this session, the first session of this afternoon. Let us thank, first of all, Ville, Andy, Irfan, Marco, and Ron for your participation and your sharing your competence and your insight on this very challenging topic. Thank you to all of you. But I want to thank you also the attendants for your participation and also for the contribution through a very live question and answer session. Let me remember that now it's time for the coffee break, but there is also the possibility to look at the poster session. The next session will begin at 4 p.m. here in this room. And please remember, at the end of the second session, we will have the industry night. So please attend in the ground floor and also the parallel session in rooms M2 and M3. We will close the industry night session at 20 this evening. Thank you.
Together want to go, together want it's my new obsession. Yeah, pink, it's not even a question. Pink on the lips of your lover. 'Cause pink is the love you discover. Pink as the pink on your cherry. Pink, 'cause you are so very. Pink, it's the color of passion. 'Cause today it just goes with the fashion. Pink, it was love at first sight. You're pink when I turn out the light. Pink gets me high as a kite. And I think everything is going to be alright, no matter what we do tonight. Pink could be my flamingo. 'Cause pink is the new kind of lingo. Pink like a deco umbrella. It's king, but you don't ever tell her. Pink, it was love at first sight. You're pink when I turn out the light. Pink gets me high as a kite. And I think everything is going to be alright, no matter what we do tonight. I want to be your lover. I wanna wrap you in rubber. As pink as the sheets that we lay on. 'Cause pink is my favorite crayon. Pink, it was love at first sight. You're pink when I turn out the light. Pink gets me high as a kite. And I think everything is going to be alright, no matter what we do tonight.
I'm gonna tell you something I know you ain't gonna wanna hear. I'm letting go, I'm letting go, I'm letting go. I'm gonna tell you something I know you ain't gonna wanna hear. I'm letting go, I'm letting go, I'm letting go. I'm letting go, I'm letting go. Ain't no use pretending. I'm gonna tell you something I know you ain't gonna wanna hear. I'm letting go, I'm letting go, I'm letting go. I'm gonna tell you something I know you ain't gonna wanna hear. I'm letting go, I'm letting go, I'm letting go. I'm letting go, I'm letting go.
And decides after 70 years that what he goes for is to unlock the door. What does around him criticize and sleep? And through a fractal on the breaking wall, I see you, my friend, and touch your face again. Miracles will happen as we dream. That we're never gonna survive unless we get a little crazy. Now we're never gonna survive unless we are a little crazy. Yellow people walking through my head. One of them got a gun to shoot the other one. And yet together they were friends at school. If all were there when we first took the pill. Maybe, maybe, maybe miracles will happen as we speak. That we're never gonna survive unless we get a little crazy. Now we're never gonna survive unless we get a little crazy. Now we're never gonna survive unless we are a little crazy. In a world full of people, only someone who fires in the crazy. In a sky full of people, only someone who fires in the crazy. That we're never gonna survive unless we get a little crazy. Now we're never gonna survive unless we are a little crazy. Now we're never gonna survive unless we are a little crazy. Listen to crazy. All I could ever be to you is the darkness that we knew, and this regret I've got accustomed to. Once there was the right national debts. 'Cause as we kiss goodbye, the sun sets. So we are history. Your shadow covers me. The sky above ablaze that only love see. He walks away. The sun goes down. He takes the day, but I'm grown. And in your way, in this bluish way, my tears dry on their own. He walks away. The sun goes down. He takes the day, but I am grown. And in your way, in this bluish way, my tears dry on their own. Walks away. The sun goes down. He takes the day, but I'm grown. And in your way, in this bluish It's another tequila sunrise, staring slowly across the sky. Say goodbye. He was just a hired hand, walking on the dreams he planned and tried. The days go by. Every night when the sun goes down, just a night a lonely boy in town. She's out running round. She wasn't just another woman, and I couldn't keep from coming home. It's been so long. Oh, when it's a hollow feeling, when it comes down to dealing with friends, it never ends. Take another shot of courage. Wonder why the right words never come. You just get numb. It's another tequila sunrise. This old world, it looks the same. Another frame. Cry, come to me and cry. I know, it's not easy. Your heart is aching, but so is mine. But so is mine. How can I tell you why? For so long I've been thinking. Now I know I can live a lie. Can live a lie. They say true love lasts forever. If we want it, there will be waiting a second chance, baby. But now we need time to learn, time to understand. Don't stop, cause it's better now. When I still love you, don't say goodbye. Don't say goodbye. They say true love lasts forever if we want.
Ladies and gentlemen, let's get started. Please have a seat. We are now at 16:00. We are going to start with the session 1.3 of the design and technology development of small modular reactors with chair from Mr. Chirayu Batra and Mr. Angi from the United States. Chair, please.
Good afternoon, everyone. I'd like to welcome you to this session titled Design and Technology Development of Small Modular Reactors. My name is Anaga Iyengar from the U.S. Department of Energy's National Nuclear Security Administration, and I'll be serving as one of your co-chairs today. I'd like to invite our other co-chair to introduce himself.
Thank you. My name is Chirayu. I'm the co-founder and CTO of 92 Ventures.
So this session focuses on the latest advancements in the design, development, and deployment of SMRs with an emphasis on innovative technologies, performance optimization, and global progress. So this session will include 6 oral presentations of about 12 minutes each and will be followed by a Q&A session at the end. So to open our session, I'd like to introduce our first presenter, Piyush Sabharwal from Idaho National Labs, who will present on the experiment and modeling efforts to support development and deployment of advanced energy systems.
Good afternoon, everyone. All right. Thanks, Anaga. Thanks, Chirayu, for the introduction. Let's see if this works. All righty. So, as we've been hearing on SMR design development throughout the plenary session, the other talks, I'm going to primarily focus on experiment and modeling efforts that are supporting the development and deployment of advanced energy systems. I call it advanced energy systems because in my talk I'm going to be covering SMRs, microreactors, and other thermal energy systems. I'd like to acknowledge my co-authors on the list. They're all from Nuclear Science Technology Division at INL. And again, it's thankful for the opportunity to present here in front of all of you. So as I mentioned, I'll be focusing my talk on 2 different areas. Firstly, I'm going to talk briefly about the modeling and simulation tools that have been developed at INL. How do they support conventional nuclear reactors, and what efforts are going on to support SMRs and microreactors? And then I know a few times people have talked about verification validation. That's very essential. So what experimental test beds do we have available at Idaho National Lab to support that need? So firstly, talk about modeling and simulation being developed at INL. The first tool that I'm going to bring up here was developed many decades back. It's called RELAB 5 3D. It's a thermal energy, it's a system code. So as it says, basically you can run it for understanding the system dynamics and also accident scenarios. It is, accepted by NRC. It basically started in 1979 and went through rigorous V&V effort before not only US, but globally it was accepted as the system code of choice to study thermal hydraulic systems. So again, it basically has verification test suite developed in 2014, and we keep updating the verification validation test bed and coming up with new versions of RELAB 5 as the need arises. Apart from conventional reactor systems, it supports pressurized water, PWRs, BWRs, the conventional reactors, heavy water reactors, high temperature gas reactors, supercritical water reactors, liquid metal and molten salt reactors. In its library, it has 31 fluids. And as I mentioned, apart from conventional, we are working with a lot of companies. A few of them I've mentioned here that we're supporting in their design and development effort. The second last bullet up there is the MARVEL and PCAT. I'll get into that in little detail. MARVEL is a nuclear, microreactor being designed and developed at Idaho National Lab. And ATR is one of the crown jewels of INL, which is Advanced Test Reactor, one of its kind in US. So apart from that system hydraulic code, we have been developing this tool called Move Space Tools, in which we have high fidelity physics along with component scale and plant scale. So what happens is, in thermal systems, normally you're mainly focused on thermal hydraulics. But this multi-physics tool provides us the availability to not only study the thermal hydraulics, but you can look at neutronics, you can look at fuel performance, you can look at structural dynamics, and more. So now you're getting the whole physics from different areas in a coupled fashion. So this basically talks about the fidelity and computational cost, all the way from 0D to large eddy simulation and DNS. So as you can see, we can go to that much detail as required for the problem. We maintain our VNV. It can do, of course, coarse mesh CFD. It has sub-channel and thermal hydraulic module. Fluid types we look at is incompressible, compressible, and weakly compressible. We have successfully designed and developed a MEC-RE model, which is a molten chloride reactor experiment, in which we not only look at the thermal system dynamics, we also look at the chemistry effect, because molten salts, you got to take that into account to understand how does chemistry play into effect, right? And a few of the examples I mentioned on the slide. Examples of, so basically how do we solve? We solve the Navier-Stokes cases, validate. As I said, we keep increasing our database on validation to gain confidence in the tool. And as we do that, we make sure that we are conserving the required equations of mass, momentum, energy, and look at a benchmark compared to the codes that already exist in this arena to see how we are doing in comparative fashion. We have hundreds of regression tests that we do on this. Sorry, I'm kind of going fast because I would like to cover a few things, and then if there are more Q&A, I'll be happy to entertain those questions. We look at both flow, laminar, turbulent, and also transition regimes. And these are the validation cases. As I mentioned earlier, these are novel concepts. We're looking at liquid metal, molten salt, and gas-cooled reactors, so the validation database is limited. But whatever gets available, we always try to make sure that we do validate the code and the module that we implement. So that's all good, but when we talk about these novel first-of-a-kind concepts, we need to make sure we have a test bed to basically perform a few things. Reduce uncertainty, further verify and validate our assumptions, which goes in these models, right? How do we do that? So first test bed I'm going to talk about is called SPHERE test bed, which is primarily basically we're looking for is for heat pipe test facility. This is a 20 kilowatt setup. You can go up to 90 degrees Celsius. As you know, for some of the advanced energy systems, people are looking at heat pipe as a passive means to cool or take away the energy. So how do we do that? We want to make sure that we have capability to understand steady state and transient behavior, right? So we want to have that access so we can manipulate or change the conditions to understand how the performance would be for the system. How do we get rid of the heat in an effective manner? So this facility provides us for testing our heat pipe capability. First is a little higher scale. That was 20 kilowatt. The next one is a 250 kilowatt. It's called magnet test bed. It's a 250 kilowatt electrically heated microreactor facility in which we can test thermal hydraulic concepts or test articles. We use air, inert gas, or mixture of helium and nitrogen. It goes up to 2.2 MPa, and the maximum temperature we can attain is around 750 degrees Celsius. Now, what makes it unique about this test bed? If you look at this picture here, which is shown on the screen, this is in a facility at INL called Energy System Lab. It's co-located with TEDS and HTSE. TED is the thermal energy distribution system, which is nothing more than, it's like a packed bed energy storage. The next facility next to it is called high temperature steam electrolysis. Both of the facilities are operational. And this one I'm trying to show is, this is the reality. In magnet is we have power source coupled, which can be coupled to an energy distribution system, energy storage, further being coupled to high temperature steam electrolysis, which basically is a 25 kilowatt unit which produces hydrogen. So here, one place I have a source. Second, I can store, understand the charge and discharge rates. And third, it will be coupled to the real load. So now you see how a grid would work, right? When you have a power source, storage, and basically my load. This is a very, easy pictorial because the real facility is more like this. But this might, basically being so busy, it's hard to see what all is going on. There's, apart from all the testing I said, there's a lot going on in this facility with EV charging, distributed systems, and microgrid. So those are non-nuclear experiment test beds. right? So now talking about nuclear test beds, which is a Marvel reactor that we're basically designing and developing. It's 85 kilowatt thermal reactor, DOE authorized, and so that's an ongoing effort at INL. Basically, it's a natural circulation crude, uses sodium potassium eutectic, inherently safe, uses used hydride as the fuel. So as I said, right, so basically before we deploy that, before we go to critical state, we want to understand the thermal hydraulic behavior in the system. Now, how do we do that, right? We can't just solely rely on the codes that's available. So we developed at INL, it's a test article called PCAT, which is Primary Coolant Apparatus Test at MFC. As I said, it uses sodium potassium eutectic as the coolant, which is alkali metal. Handling an alkali metal of that much amount is not, you can't do that on day-to-day, so you need a special facility which can handle that much alkali metal. So though we built it, it was sent from Idaho Falls, Idaho, to creative engineers in Pennsylvania for testing, so we can understand how well we predict using our thermal hydraulic codes. We understand, are we able, as I said, it's a natural circulation cooled reactor. We need to make sure that we are able to, first of all, develop natural circulation, secondly, maintain natural circulation in this alkali metal reactor. So this was sent, so basically the data we gathered, we were able to compare that with Relab 5, which was used as our thermal hydraulics tool to do the modeling for Marvel reactor. And as I said, the initial startup was on September 19, 2023, with demonstration of natural circulation power generation. So doing such efforts helps us reduce or de-risk the risk involved in these novel concepts for industry, right? Apart from Marvel, we have a couple of other test beds that's being developed. One is called DOME, which basically is a 20 megawatt setup. It's basically reestablishing capabilities of existing infrastructure. So the dome that you see up there, the silver dome, is basically from EBR 2. And the one on the right-hand side is basically a 500 kilowatt heat rejection system. It's in the Lotus test bed facility. So now, people, as you see, many companies are out there with novel concepts, right? They have the concept maybe verified using system codes, but they need a place, and unfortunately, not all places have the infrastructure. Being the nuclear lab for US, we have the infrastructure, or we are developing the infrastructure that we don't have currently, to basically make sure that we are able to de-risk the challenges, reduce uncertainty, and provide the required data to gain confidence and help, once you have the data, to basically support the licensing activities for the companies. Again, I want to reemphasize, as a national lab, we do not design, we just assist in the development. Okay, we don't really go and design a concept for a vendor. They have the design, we just make sure that if they work with us, we basically work with them to, as I said, do initial testing that they might not be able to because of lack of infrastructure. So here are a few of the companies listed that we are working with for the dome facility, and those are going to be housed at INL. This is how next decade INL looks like. I know this is a pretty busy slide. It basically houses like a lot of DOE, DOD projects. And then towards the end in 2030, we are working with SMR 300 megawatt electric, the whole tech team, to again do some testing for them. So we are currently developing a separate effect test and integrated effect test because they have some novel designs that they would like to test, and again, as I mentioned, reduce uncertainty in the system. So we are working with them hand in hand to do that. And other concepts that you see are basically, this is when we anticipate the deployment to be. This is first of a kind. We're working with Westinghouse, eVinci, and other reactors that I mentioned to make sure that we are able to do the testing and help them with the first of a kind demonstration. So looking at the time, the key conclusions that I would like to state is really we have exciting challenges ahead as a nuclear industry, nuclear community. Still, we need to look at innovative ideas to bring down the cost as much as possible. I know one of the previous sessions, somebody talked about AI, ML, maybe advanced manufacturing, for looking at some novel, maybe heat exchangers or steam generators for components. And then key thing for next era is demonstration. The successful demonstrations needed to gain utility, regulate, and public confidence. These are novel concepts, first of a kind. If you're not able to demonstrate, basically, we can't successfully license these just based on what a thermal hydraulic tool might say. So demonstration is the key. Thank you all. That's all.
Thank you, Piyush. So we'll take the Q&A at the end of the session. Now, let me invite Mr. Paul Gauthier from France. He's going to talk about Hexana, a sodium-cooled fast reactor. Paul.
Okay. Hello everyone, I'm Paul Gauthier, CTO of Hexana. Hexana is a French new startup developing a sodium advanced modular reactor for sustainable industrial decarbonization. The startup was funded 1 year ago. So why this project? If you're here, you know that there is no climate solution without industry decarbonization because it's a lot of fossil energy. 90% of the industry energy is driven by fossil fuel. What you may not know is that most of this energy is heat energy, not electricity. And among this energy, 50% is high temperature graded heat, above 400 degrees. So basically, tackling the climate change is decarbonizing the industrial need for heat, high temperature heat. So why does a Gen 4 SMR, sodium fast reactor technology, is a good candidate among the other Gen 3 SMR? Why developing Gen 4 SMR? First of all is Gen 4 SMR delivery of the high temperature heat to the industry in complement to electricity. You can drive direct process heat in a wide temperature range up to 500 degrees that you may not able to do with Gen 3 SMR. You can produce also heat, electricity, and hydrogen with a very good efficiency, and it also enables heat storage for flexibility and decoupling issues. I will explain why. But it's also a sustainable solution. As you may know, we develop Gen 4 solution for sustainability because it's good for the climate and ecology. We use spent fuel as a resource. We don't need the uranium mining. That means less waste, less water, less environmental impact. It's good for countries because of the energy independence. It's good for customers, for industry, because it's a stable operation cost and long-term guaranteed price. We don't depend on the natural gas prices, on the uranium prices. And it's good for the nuclear industry because it guarantees that the nuclear industry will be sustainable one day. No, why does this Gen 4 sodium fast reactor is a good technology among the other Gen 4 system? Because the sodium fast reactor is the most mature and credible technology among all the Gen 4 system. We have a core-proven technology all around the world, especially in France, with a lot of experience with Rhapsody, Phoenix, and Super Phoenix, the biggest sodium fast reactor ever built, operated, and dismantled. We have fuel and materials already qualified, ready for use in such a reactor, and we have the ecosystems, basically in France, with big nuclear ecosystems in sodium fast reactor. So now, what is Hexana? Hexana is not only a reactor, it's an energy system, world energy system, and we provide innovation in the modularity, the flexibility, and the integration. We produce the energy with two sodium fast reactors, 400 thermal megawatt each. We provide this heat to a thermal heat storage module, which provide flexibility, but also the decoupling between the nuclear part and the industrial part. And we provide the tailor-made energy, heat and electricity at various levels of heat to our industrial customer. Our customer can be the heavy industry, steel making, hydrogen, chemicals, ammonia, e-fuel, etc., desalination, and so on. So the main interest of the solution is that on the nuclear part, we aim to be as modular as possible, as standard for industrialization and serial production. And on the industrial part, we want to be as tailor-made as possible and to deliver the right level of energy at the right time. So the heat storage allows that. So here is our balance of plant architecture. We have the reactor, sodium circuit, sodium secondary loops driving the heat up to more than 500 degrees, and a classical storage salt loop with nitrate salt, with a hot tank and a cold tank. The goal is to provide all the flexibility with this system and not use the reactor for flexibility. So the reactor is operated as a base load, which is favorable for lifetime of the reactor, safety, simplicity, and so on. And we address the flexibility with the storage system. After that, we have a classical Rankine PCS system, and all that we want to do is basically with this system where to supply the heat to the industrial. In the storage, in the PCS system, at which level of temperature, without decreasing the gross electricity output. So basically for each use case, we try to optimize our system. A way to use what we do at Hexana in terms of modelization, we modelize our storage system and Rankine PCS system, and basically we calculate the gross efficiency with ThermOptim software, and also with a Modelica simulation for the transient. Because what will be important is that to demonstrate that the heat storage will do its work of a kind of a buffer between the nuclear part and the industrial part. We must demonstrate that whatever happens in the nuclear part, the industrial has not an emergency scrum in this in his factory, and on the other side, we must demonstrate that whatever happens in the industrial site, the reactor will be fine. So thanks to the storage system, we believe that it will be feasible, and we want to demonstrate it with a simulation. In this slide, you see, for example, a theoretical case when we have a small direct heat demand, for example, a 30 thermal megawatt with two temperature difference. So we have a choice is to take the heat directly in the heat storage, or to modify the Rankine PCS system to provide the heat. So we test a multiple configuration, and the goal is to take the pros and cons of the modification of the Rankine PCS or the direct heat with the storage system. In this case, when we have a little heat supply in comparison to the whole energy system, we think it's better to take the heat directly in the heat storage system, in the hot tank, and to have a classical Rankine PCS system. It's better for CapEx and OpEx reason. So that is the kind of study we make for our end user and future customer, as we hope. So now, what is the interest of the Hexana storage system? It has interest for the industrial needs because of the flexibility, but also because of the decoupling between the nuclear site and the industrial site. I don't know any end user who wants to have a nuclear reactor in the middle of its factory. They want a nuclear reactor near its factory with a big contract for energy supplies, but they want a decoupling between the nuclear part and the industrial part. And it enhances the siting possibilities because we can transport direct heat for 1 kilometer or two, so we are not mandated, we have not the obligation to put the reactor in the middle of the factory. In terms of safety, it's also useful because of this decoupling, but also because of our technology. You know, it's a sodium fast reactor, and we have a water steam Rankine PCS system. You know that sodium and water are not good friends, so to introduce a heat storage system, it allows us to separate completely the sodium and the water. And not only for chemical reasons, but also for pressure reasons. We have a nuclear island without any pressure, which is very favorable in terms of simplicity and operability. It's also an economic reason to have this storage system. We sell energy when it's expensive, we store when it's cheap. We can have also public subsidy for the grid security and the capacity that we add for the security. And it's a system, an additional system, but in fact it's an overall capex reduction because we excluded the pressure part from the nuclear island, which is very interesting in terms of cost. And the maturity, these systems are very well known in the solar energy, thermal solar energy. So it's not a problem to have this kind of system, a gigawatt scale system. We also study the different backups or innovative tracks, but we believe that high-terail storage system can fit our solution. So for this storage system, we design it either in a buffer mode, buffer approach. It's only to have this kind of buffer between the two and to delay the import of export of power to or from the grid. But we can have a bigger storage system to have a load following approach and to follow the demand in electricity of the industrial and minimize the import of an export link to and from the grid. So basically our studies is the optimization of the overall system for each use case, without over-investing in additional system. So, in conclusion, why is Hexana relevant? A relevant solution to decarbonize industrial hubs. So, it's compatible with industrial needs. It's a relevant size and power. It's a rather large power. It's one of the biggest SMR. It's two reactors of 400 thermal megawatts. So, it's rather large capacity for large and heavy industries. We can have continuous energy delivery thanks to the module tuning. We have two modules, so when one reactor is in maintenance or fuel reloading, the other can operate for the industry. And we have an integrated production of electricity, heat, or even hydrogen or other byproduct like desalination for each use case. It enables to meet our climate target. We have a higher efficiency, energetic efficiency than Gen 3 reactor, less need of water for electricity production, and last but not least, it's ultra low carbon energy, less than between 2 and 3 grams of CO2 per kilowatt hour, which is thanks to the MOX utilization, thanks to the fast reactor physics that avoid the importation of uranium. And then it's a reliable, predictable, and growing energy price on several decades. We don't depend on the uranium market evolution, so it's geopolitically resilient technology. We can have a base load nuclear operation and high flexibility thanks to the storage. So it's an optimized plant for increase the revenue of the operator and increase the lifetime of the operator. And last but not least, with our storage system, it is the integration of renewable on site. We can absorb the intermittency thanks to the heat storage. Thank you for your attention.
Up next, we have Guido Mazzotti from Italy, who will talk about experiments and modeling of the passive decay heat removal systems with plate-type compact steam generators.
Yes, thank you for this introduction. So good afternoon, everyone. My name is, My name is Guido Mazzotti, and I'm a PhD student from Politecnico di Milano in Italy. First of all, I'd like to apologize because, as you can see from this slide, I was not involved in this work, but since none of the others were available, I will try to present these activities on behalf of Andrea Missaglia. Here you can see the contents of the presentation, which is devoted both to the experimental and modeling part of a passive decay heat removal system and a plate-type compact steam generator. Let's start with the experimental part of the work. The objective, was to study the facility created for the European-funded ESWR project, from which we heard something in the session before. And the project was devoted to assess the let's say, light water safety of light water cooled SMR using both experimental and analytical methodologies. And as part of this project, a dedicated facility has been designed and built in Siet, in Italy, in Piacenza. And this facility comprises a passive decay heat removal system working in natural circulation conditions. The facility consists of three main systems. The primary system, which can operate either in single phase or in two-phase forced convection. The secondary side, which relies on two-phase natural circulation, which is driven by the heat exchange in a compact steam generator. And lastly, we have the tertiary part, which consists of a pool that essentially operates at atmospheric conditions and serves as the ultimate heat sink using an in-pool heat exchanger. So, before moving to the actual part of the work, I'd like to speak a little bit about the compact heat exchangers, since they offer significant benefits, including a small footprint and high power densities. And this feature leads to reduced costs and enhance the overall efficiency of SMR designs. Also, this technology is key, or already key, in various industries, such as transportation, energy, oil refining, and also hydrogen production. And when it comes to integral type SMRs, of course, space optimization is essential. And in this case, compact heat exchangers are crucial for minimizing the heat transfer volume. And in addition, they also lower the manufacturing costs, helping SMRs to compete with large-scale reactors that, of course, leverage on economy of scales. And but however, there are still some challenges, including the limited use in liquid boiling applications and the need to have established correlations in, let's say, in operating conditions of nuclear reactors. In this section, we have the selected experimental tests. The experimental test matrix consists of 81 tests organized in 7 distinct groups. The main goal is to assess the effects of various factors on the operation of the decay heat removal system. And specifically, in this work, we examined the influences of primary pressure, temperature, and secondary side filling ratio, as well as the presence of non-condensable gases. First of all, it's important to clarify that the filling ratio is defined as the mass of liquid actually contained in the circuit and the total mass that can actually fit in the same circuit. And then to dive deeper into the testability of the decay heat removal system, we selected 2 tests that you can see listed here, 99C and 100C, that stem from the SMR database. The first one involved reducing the filling ratio from around 60 to 20% while maintaining the temperature constant. And this adjustment was crucial to understand how variations in filling ratio affect the stability of the system. Then test 100C, so the filling ratio dropped below 15%, which led to mass flow oscillations. And subsequently, the filling ratio increased to about 18%, achieving the initial stable conditions. In this slide, you can see the RELAP 5 model of the SMR facility, which has been developed both for pre-test and post-test analysis. We employed the RELAP 5 mod 3.3 code, leveraging on the expertise from both CIET and INEA, gained from the SPEC-3 facility. And the model consists of a nodalization composed of 3 hydrodynamic systems. The primary system, including the separator and the CSG. Then we have the secondary system with the CSG and the in-pool heat exchanger. And lastly, the surrounding pool, which is the area that serves as the heat sink of the system. In the model, these systems are thermally coupled by means of some heat structures, and in addition, to ensure that the model reflects the expected operational conditions, we made some specific adjustments, on the one hand to the pressure loss, but also to the heat transfer factors. And these modifications were essential to align the model with the experimental dynamics of the facility. Last but not least, there are some key modifications implemented to the model needed to enhance the accuracy of the predictions. Okay, now we can delve deeper into the results obtained with the model and compare them with the experimental measurements. For test 99C, the code effectively predicts the experimental data, demonstrating a strong correlation with only some minor discrepancies. And you can see this in the figure above, where the left side shows the primary CSG inlet temperature, outlet temperature, and on the right side you can see the inlet temperature. The alignment between the model results and actual measurements shows the reliability of the model in simulating the behavior of the system under the tested conditions. Then for test 100C, the code aids in understanding the phenomena behind the onset of non-condensable gas instability. And while the model provides some valuable insights, there are some discrepancies that can be noted in the predictions. In figure 6, for example, we have the left side showing the mass flow rate and the right side the secondary pressure. And these differences highlight the complexity of the phenomena occurring during the test and indicate further area of investigation. Here we explored the chain of events that led to the onset of natural circulation instability. As the filling ratio drops below 15%, the liquid phase can no longer enter the CSG. And at the entrance of the CSG, there is a loop seal develops, and with a stratified two-phase flow. And in this situation, the liquid occupies the lower portion of the pipe, while the vapor enters the upper part of the CSG. And consequently, we have superheated vapor exiting the steam generator, leading to no further generation of condensate in the in-pool heat exchanger. As the vapor passes through the cold leg, it does not provide sufficient momentum transfer to allow the liquid to re-enter the CSG. But in any case, this momentum transfer is enough to cause some oscillations of the returning liquid, which is unable to re-enter the CSG and reverses its flow. So this sequence of events highlights the intricate dynamics of the natural circulation and the mechanisms that can lead to instabilities under these specific operational conditions. And understanding this phenomena and these processes is also, of course, essential for improving the reliability and the safety of passive safety systems. RELAP 5 is unable to catch such complex phenomena, and one significant factor is the behavior of the vapor velocity in the simulation, of course. And because in the RELAP 5 simulation, the higher vapor velocity leads to the formation of slag flow, which pushes the liquid into the compact steam generator. However, the experimental data indicate that a stratified flow exists in the loop seal rather than the slag flow predicted by RELAP 5. And this difference in flow patterns contributes to observe discrepancies, of course, for the test 100C. Additionally, the RELAP 5 model shows some spikes in exchange power, secondary pressure, and temperature oscillation, which are not present in the experimental data. So, in conclusion, going back to SMR, the project significantly advanced the licensing of light water-cooled SMRs through experimental and analytical efforts. And a key achievement was the design and the construction of the facility in Siet to study the performance of the passive decay heat removal system. And the key findings from the test, 99C and 100C, successfully predicted the experimental results, both quantitatively and qualitatively. However, there were some discrepancies observed on the secondary side pressure, temperature, exchange power, mainly during periods of two-phase flow instability. And these discrepancies can be attributed to uncertainties related to the internal geometry of the heat exchanger, as well as variations in heat transfer behavior and pressure losses within the system. Here you can see the references of the presentation. Thank you for your attention.
Thank you. Great overview. Thank you very much. Very interesting modeling and simulation work as well. With this, I would like to invite our next speaker, Professor Igor. He's going to talk about, from Ontario Tech University, he's going to talk about the current status of SMRs development.
You can see our co-authors for this presentation. And here is major references. This is our Handbook of Generation 4 Reactors, published in 2023 and updated in January of 2024, and some other sources which we have used. I will start from general things, what we have as of today in nuclear power industry, and after that to move to specifics and what we have with SMRs. As you can see, currently we have 446 nuclear power reactors connected to grids, but not all of them, of course, operating. At least in Japan, from 33 reactors left from 54, only 10 pressurized water reactors in operation, but they are still included here. The largest group, it will be pressurized water reactors. I am comparing number of reactors, installed capacities, what we have as of today, and what we had before the Fukushima Daiichi severe nuclear accidents. And last two columns, it will be force command units. Due to this bright future, definitely going for pressurized water reactors. It's unbelievably large number of reactors currently under construction and planned to be built extra. For boiling water reactors, it's not very good situation. They dropped down quite substantially from 92 to 60 reactors, and currently, except Canada with Hitachi and GE, which building boiling water reactors, small modular reactors, BWRX. Eventually, in the world, no one building boiling water reactors, at least for now. Number 3, it will be pressurized water reactors. It's still not too bad, but as you can see, it's not so significant development either. It's only maybe 16 reactors, and it mainly will be built in India and some other countries. Number 4, it's newcomers. It will be well-known reactors, and actually these AGRs, it's carbon dioxide cooled. Nuclear power plants have the highest thermal efficiency among all other reactors, around 43%. However, United Kingdom have not done any development for last 40 years with these reactors, because unfortunately all of them will be shut down within the next 5 to 10 years. Number 5, it's newcomers. It's two small modular reactors. High temperature reactors pebble bed module from China. It will be second highest thermal efficiency, around 42%. And number 6, it will be light water graphite moderated reactors, all of them in Russia. Unfortunately, one RBMK exploded at Chernobyl nuclear power plant. Due to this type of reactors also will disappear within maybe next 5, 10, maximum 15 years. And number 7, it will be liquid metal fast breeder reactors. Currently, we have only 3 sodium cooled fast reactors in operation, 2 in Russia and 1 small in China. And also only 3, 2 in China and 1 in India, possibly will be on the market quite soon. However, we have also good news for small modular reactors. We have lead cooled fast reactors at the Brest OD300, which currently under construction in Russia. And the gas-cooled reactors, sodium-cooled fast reactors, and lead-cooled fast reactors, it's definitely concepts from generation 4 reactors. If you look at the major countries where we have in red means decreased within this 13 years, where we have green increased, definitely China has real renaissance in nuclear compared to all other countries. It's unbelievable. Within 13 years, 45 reactors put into operation. And also in some other countries like Russia, South Korea, India, we have also some number of new reactors appeared. If you look who is doing what currently in the world, 3 countries will be ahead of the rest of the country. It will be Russia, China, and India. Russia and China, approximately around 30 reactors will be built and planned to be built there. Russia mainly building outside country, China building inside country, India also around 19 reactors, also building mainly inside country. All other countries definitely not can be comparable because it's going from 4 to maybe 1 new concepts. What we have to remember that it doesn't matter what we will do in nuclear, number 1 priority is safety. This is all current reactors in operation. We have all these reactors from 1969. It's only 2. In dashed lines, it's when we have 3 major nuclear accidents. Of course, the most severe one, it will be Chernobyl nuclear power plant disaster. And as you can see, our glorious days in nuclear power industry were exactly from 1985 till 1989, where almost 120 reactors have been built and put into operation. Unfortunately, after that, we dropped very significantly, and in 2005-2009, it was around maybe only 16 reactors put in operation in 5 years. We started to recover after Chernobyl, and Fukushima Daiichi nuclear power plant disaster happened. However, it significantly affected Japan and some other countries, but still, we started to move up. And I was really surprised that within last 5 years, from 2020 to 2024, we dropped down 1.5 times. It's really not a good trend for all of us. This is thermal efficiencies. What I would like to show is that, first of all, now in nuclear, how it was always in thermal power, driving force is thermal efficiency. And we definitely have significantly lower thermal efficiency for all nuclear power plants, especially for light water-cooled and heavy water-cooled nuclear power plants. It is definitely we have to do something with that. Last, the bottom 2 rows, it will be thermal efficiencies of Rhythm 200M, which currently under construction nuclear power plant in in Russia. And the last one, it will be operating 2 small modular reactors, actually the first one by Russia on as floating nuclear power plant. You can see it's only 26%. And Rhythm 200M will have around 31%, which is significantly low compared to any other reactors. When we're looking at the small modular reactors in general, we have estimated that we have around 108 concepts, and definitely we have to understand that this vast majority of concepts not yet designs and very few in operation. These concepts can be spread in like water-cooled SMRs, land-based, 33 water-cooled SMRs, marine-based, 7 high-temperature gas-cooled, helium-cooled, 21 fast neutron spectrum SMRs, it means sodium, lead bismuth reactors, 26, molten salt reactors, 17, and other reactors will be 4. We're talking about a couple of concepts with heat pipes. From all these reactors, only 2 concepts and 4 reactors in operation. By countries, USA number 1, 28 concepts under development, Russia 15, China 13, and after that Japan, Canada, and some other countries behind. No, I will not spend time on this one. It's just all basic parameters of current reactors, and lower table is all Rankine cycle. Currently, all nuclear power reactors connected to Rankine cycles at different options. If you look at the reactors to the left, LT40S Rhythm 200M, Rhythm 200M proven as a propulsion reactor at the icebreakers, LT40S in operation as first 2 reactors on a barge. You can see in red, more or less even already reactor under construction and completed design. Thermal efficiency is not very high. It's around 30% approximately. In red, I put some specifics. One of such specifics, it will be that in operating KLT40S and in rhythm 200M, it will be relatively high enrichment. In KLT40S, it's 18.6. It's at the bottom row. And in rhythm 200M, up to 20%. Of course, it means that very few countries can manufacture such fuel. And this is very special things for that. Also, these two SMRs, they have no steam reheat in Rankine cycle, due to this also contributed to quite lower thermal efficiency. However, they have slightly overheated steam at inlet. And for SMRs like NuScale and Holtec SMRs 160 and BWRX, the companies decided to go with natural circulation during regular operations. And also, I don't know any nuclear power reactors as of today which this natural circulation has been proven before. Due to this, we have to watch how it will be done. And we have also some parameters of the HTR-PM in China. And after that, what is under construction right now, it will be a lead-cooled fast reactor, Brest OD-300 in Russia, in Siberia, and it can be breakthrough if they will put with breeding operation, with breeding ratio 1.05, definitely and possibly the nuclear power can be from non-renewable source, can become a renewable source of energy. It is, thank you very much.
Thank you. Up next, we have Nuri Trianti from Indonesia, and she'll be speaking about the performance optimization analysis using an HTGR code package.
Thank you very much, Anna and Shirayu. Good afternoon, everyone. So I'm Nuri Trianti from Research Center for Nuclear Reactor Technology, National Research and Innovation Agency. I will be presenting regarding our research preliminary analysis of initial criticality for Polluit 40 using HTGR code package. So this is the outline of my presentation. And then, yeah, Polluit 40 is a 40 megawatt thermal high temperature gas cooled reactor, or HTGR, designed for cogeneration, producing both electricity and heat. Its design focused on passive safety and ensuring high operational safety. In our study, we used HTGR code package, or ACP, to simulate initial criticality and perform the temperature coefficient simulation based on IAEA Tech Doc regarding the evaluation of high temperature gas cooled reactor performance benchmark analysis of HTTR and HTR10. This B1 cases involving simulation at 20 degrees Celsius, both helium and air atmosphere, and the B2 case is varied core temperature from 20 until 250 Celsius degree. So now let's take a look into the Polluit 40. We call this reactor is Polluit, an abbreviation of Pembangkit Listrik dan Uap untuk Industri in Indonesian, so which not only generates electricity but also steam, which can be utilized by industrial needs. So the reactor core is cylindrical with the diameter of 180 and the height of 197 centimeters. A reflector and thickness and the other dimension are carefully chosen to optimize safety and performance. The reactor used a pebble bed fuel with uranium enrichment of 17%. And the refueling scheme follows of the once through then out, or OTTO method, which simplified fuel management. So in general, the reactor design, graphite serves as the primary core structural materials, primarily in the top, bottom, and the side of the vessel, which contains the ceramic core structures. The zone division for the two-dimensional reactor physics calculation model are shown on the figures. And then the calculation method, we utilize the HTGR core package or ACP, which developed by Zurich University and provided by Encore IAEA. So ACP is a comprehensive computer code system designed to simulate various aspects of HTGRs in the integrated manner. This tool aids in design, safety assessment, and operation of HTGR's reactor core. The ACP is modular, consisting of several interworking modules that simulate a different aspect of an HTGR as shown in the figure. So HTP includes several key modules such as TRISA for neutron spectrum calculation, and then TNT for burn-up calculation for fuel depletion, and SOFWEL for simulating fuel movement. So for this study, we focus on the initial criticality simulation using TRISA, TNT, and SOFWEL module. So in this study, a validation calculation was conducted for the fluid reactor with power variation starting from 10 until 40 megawatt thermal. The validation involves calculating the amount of loading of the first criticality in order to obtain the rigorous comparison among different power for 10 megawatt and 40 megawatt thermal. So the quantity of loading or provided in loading height starting from the upper surface of the conus region for the first criticality. Initial criticality in pebble height variation of the fluid 40 is conducted. This calculation of the K effective for different height of the core is considered variation of the power as well. Then we consider the variation of the materials properties, including the densities of the dummy pebbles, and then the atmospheres of the core, which is using helium and air. So, and using the variation of the temperature. This variation parameter input is based on the benchmark case in the tech talk of IAEA. So next, we validated our simulation by comparing K effective value under different power levels, ranging from 10 megawatt thermal until 40. So as shown in the table, this is the K effective for both the original and deviated cases remain stable. However, the deviated scenario shows a slightly higher K effective materials properties such as a pebble density and boron impurities. The K effective value is lower than air, is used as a coolant compared to that helium. This phenomenon occurs since the neutron absorption in air is relatively high compared to helium, and neutron moderation in helium is slightly higher than air. So power increase leads to slight K-effective decrease in both conditions, indicating predictable reactor behavior under varying power levels. So the figures in the slides shows the axial and the axial in fast and thermal neutron flux profile respectively at several power levels for both original and deviated scenarios. So deviated case exhibit a relatively lower axial fast neutron flux profile compared to those of original cases. Meanwhile, there are no significant difference between the original and deviated scenarios for the axial thermal neutron flux profile. So next, one of the key aspects of our analysis was determining the optimal pebble height for achieving the first criticality. Calculation of the K effective for different core loading heights was performed using ACP for fluid 40 geometry using power of 40 megawatt thermal. The calculation is aimed to find the loading amount or provide in loading height for the first criticality with K effective 1.0 something under the helium atmosphere, starting from the upper surface of conus region or 90 until 180 centimeters with no control rod inserted. So our simulation shows that a pebble height of 117 is necessary to achieve the K effective of 1.0. Is correspond to 9,162 fuel balls and 6,911 graphite moderator balls in the core. We also analyzed the pebble height affect neutron flux. Both fast and thermal neutron flux decreased as the pebble height increased. The distribution of the flux of each core loading height indicates that both fast and thermal neutron flux generally increase as the core loading height increases. This decreases in neutron flux is critical parameter in nuclear reactor design because it influences the reactor power distribution and overall performance of the reactors. And in the B1 case, we calculate K effective for the original and deviated scenarios. The K effective increased slightly from 1.0017 to 1.0118 in the deviated cases. And then the maximum flux value are nearly identically for both scenarios, which aligned with the table data showings. This suggests that while the deviated affects the fast neutron population, the thermal neutron population remain relatively along the reactor's axial length. Then next we analyze the effect of the temperature's variation on K effectives as the temperature increased from 20 Celsius degree until 250 Celsius degree. The K effective value decreased slightly in both original and deviated scenarios. This indicates the predictable reactor behavior under varying temperatures with higher reactivity observed in the deviation scenarios. The deviated scenarios exhibit marginally higher reactivity and shift in neutron behavior with an increase in thermal neutron flux and slight decrease in fast neutron flux across varying temperatures. And we benchmark the B2 cases based on the tech doc of IAEA, benchmarking HTTR and HTR10 with original and deviated scenarios towards the axial fast and thermal neutron flux profile. And the presence of boron impurities in the coolant influenced the K effective and reactor core neutron flux values. The large absorption of cross-section value in the thermal neutron spectrum has significant effect on the thermal flux neutron. Therefore, the neutron flux in the original condition with higher boron impurities tends to be lower due to boron absorption. The increase in boron concentration will not be directly proportional to flux neutron, since boron plays a role plays a role as a thermal neutron absorber. So in conclusion, we conducted a preliminary analysis of fluid 40 for initial criticality using ACP, STGR code package. And our results shows that pebble bed height with 117 centimeters is required to achieve criticality under helium atmosphere. And the deviation in materials properties such as higher pebble density and lower boron concentration increase reactivity. And the last is regarding the temperature variation further highlight the reactor stable behavior with only slight changing in reactivity across the range temperature studied. Okay, that's all my presentation. Thank you very much.
Thank you very much, Nuri. Very interesting neutronics simulations using the IAEA HCP package. Next is Piyush again, because he's going to talk on behalf of Palash Bhumik from INL on SMR current status, the development needs, and the global perspectives. Piyush.
Perfect. Thanks, Chirayu. As Chirayu mentioned that, so this is a research staff at INL and Nuclear Science Technology Directorate. Palash Bhaumik. He couldn't be here, so I'm presenting on his behalf. This talk basically would primarily provide the current status, development needs, and global perspectives. So you'll see a few of the slides that basically came from IAEA to provide the global perspective to this. So in this, I'll be talking about overview of small modular reactors. I'm sure you've seen most of the stuff because, this is SMR conference, so a few of this will be repetition, with a few of the development phases, what needs to be done, potential solutions. Status of SMRs, SMR development needs, challenges addressed, and then talking a little bit about not just the problems in hand, but solution approach, and we'll end my presentation with some main conclusions. So, as you're all aware, there's basically, if I remember right, this SMR, when it came about many years back, the definition about 300 megawatt electric, which was globally used currently, came from IAEA. And I think the world globally has accepted that and uses that as a normal terminology to define SMR as any reactor which has a capacity up to 300 megawatt electric. Clean, affordable, and sustainable energy source. There are different scales mentioned on the left-hand side about large-scale reactor going from almost to 1,000 plus megawatts. Then we have small modular reactors, and talks about the landscape area, and then goes into microreactors. Right? There are 80 plus concepts being looked at worldwide, as per the reference pointed out. 80 concepts meaning like they might be in different phases. Some might be in design stage, preliminary stage, or one of those Ds, demonstration, deployment stages. So as per that reference, I think it refers 80 or so concepts existing. So again, this is not a complete list, but these are the key major challenges, and some of them have been brought up either in plenary sessions or other speakers have brought it up. The key challenges that have been identified for accelerated deployment for SMRs, qualifying the advanced fuel reactor design. So we, as nuclear engineers and researchers, we always want to push the envelope, right? So we are trying to see how we can get more from the fuel. So enhancing or getting more out of the fuel by increasing the fuel burnup, supporting rapid scale prototypic experimentations. As I mentioned in my first talk about the novelty, right? The novelty, you cannot just use a modeling tool irrespective if it's a finite element, finite volume, or thermal system code. You gotta demonstrate at some sort of scale to basically look at the feasibility of the concept and gain confidence in your system that is being proposed. Maintaining local global codes, standards, and licensing. I'll get into that in a few minutes. And then because of the novelty and different changes, we have supply chain issue, right? First of a kind is going to have that, but once we develop a market, then hopefully we can address that. But we got to start thinking about these challenges. The effective cradle-to-grave nuclear fuel cycle and fuel materials transportation issues, and mitigating financial and environmental risk. Now, sustaining the existing commercial reactor fleet and expanding deployment of nuclear energy. So what does that mean? So advanced technologies, research is going on. We have regulatory and safety research, which is happening in parallel. I think that's the best way to approach it. You look at technical as well as you look at understanding the market economics and regulatory aspects. At the same time, you will see sometimes a thermal system code might not be the right fit for your design. So you have to look at a CFD or a high fidelity tool, because there you are focusing on a component type behavior, not a system behavior. So potentially maybe system code might not be the right approach. So looking at CFD or other finite volume ways to look at it. Again, looking at advanced fuels and materials, because now you're looking at much higher temperatures for these nuclear technologies. So we got to go through the qualification process. Do we have the codes in place to make sure that happens? And then not just stopping at fission technologies, potentially looking at fusion energy. The key thing, one of the key things that I think we all can agree upon, right? It's not a problem for one organization or one entity to solve, right? To address this need, universities, national lab, and industry have to have a synergy, have to work together to address those things. Some small-scale benchmark feasibility study, university might be the right platform to get there. Then comes the role of national lab. You take the things with where the university is led or finished at, and because they can take it all the way because of lack of infrastructure. That's where national labs come in, which they have high infrastructure available. for electrical applications and also as for radiation experiments. And then when you get to mid-TRL, technology readiness level, then industry can take it from there for commercialization aspects. So if you look at worldwide status for SMR, you can qualify SMR based on either fuel type, coolant type, power conversion type, because you're looking at, depending on the temperatures, you might be looking at Rankine cycle, in which you might have sub-pressure or supercritical water cycle, or maybe you might look at Brayton cycle for helium-cooled or supercritical CO2 cycle. And then so that is a different power conversion type. Then depending on the safety, is active or passive or it's hybrid. Sometimes in some novel concepts, the reactor is cooled actively, but the containment might have some passive safety in it. Then you have design types, as I mentioned, for water cooled. Now we heard in our plenary talks looking at various applications, not only just electricity, but process heat applications, and then also now looking at marine-based applications. And then looking at what reactor matches what sort of process application. Again, as I keep mentioning, there is novelty involved in some of these concepts or each of these concepts. So there will be some setbacks, right? But learning from those setbacks, taking this as an opportunity, and as long as we learn from it and apply, for example, we'll hear about construction delays. Of course, if those things happen, what can we learn and leverage? Nuclear industry is unique in that manner. What I mean by that is success for anybody or failure for anybody trickles down, right? You see the impact. So success for one is success for everybody. And that is true for failures as well. So as long as we learn from it and apply it, because when you look at these things, it leaves a footprint that one can follow and do better economically and efficiently. This is a phase-wise approach, again came from reference from IEA document, which talks about, unavoidable challenges depending on what phase you're in. So, for the reactor technology assessment, at feasibility study, binding and commissioning. And then this is a slide to be really proud about for INL. It's an honor to work at that place. If you look at the next decade, you're looking at demonstrating, deploying first-of-a-kind technologies. As a nuclear engineer, that's the place to be. Look at amount of experiments, amount of innovation coming from all these reactor types that all of my colleagues and researchers are working at. So a lot to learn from, and next decade or so, there'll be a lot to be shared from INL with the world. Okay, now I think in my talk I also mentioned that INL, Idaho National Lab, is the nuclear lab for US. And the reason I say that is because our heritage is the National Reactor Testing Station. That's sort of how it started. So INL has been involved in designing and developing 52 reactors. So the reactor I talked about, Marvel, was reactor 53. Hopefully we'll get to criticality in the next few years. First US city to be powered by nuclear energy is pretty close to Idaho Falls. It's in Arco. And people are not familiar with Idaho National Lab. It's a pretty big lab, having like almost 900 square miles. It's spread quite a bit, and has the infrastructure to do the testing required to meet the needs, to qualify the materials, to look at first-of-a-kind experiments. And this is basically the status, the legacy history of reactor testing at INL. This is for how it started, where we in fact had treat the transient reactor experiment facility, which we restarted because of the needs. And, so as you see, a lot has happened and a lot is happening as you go forward. This, again, I think to get the global perspective, talks about, based on the surveys, to rank the major challenges for SMR deployment. I think this also came from IEA Tech Doc report, and basically does a great job of summarizing in this map about average ranking based on surveys that they were sent out and put this together. The priorities, as said here, necessary regulatory licensing challenges, economics, instrumentation control, and proliferation resistance. Now, the key thing, why is SMR important? We need to create a secure, resilient, clean, sustainable energy future, right? So we have various directorates at INL working for that mission. So we have nuclear science and technology, as the name suggests, looking at nuclear technologies, looking at design and deployment. Then we have advanced test reactor complex, which is an irradiation facility that you can irradiate your samples. So now you can look at a sample and understand before radiation, after radiation effects, right? That's one of the unique, in fact, I term that as one of the crown jewels of INL. Then we have materials and fuel complex, which looks at, we can look at post-radiation examination to examine those things, that is irradiated ATR, and understand material characteristics even further. Then we have energy, environment, science, and technology. Now, all this technology is good. How do I take that heat away from the source? How do I make sure my grid doesn't see an impact? Are there any perturbation effects? How does my source behave, right? Looking at those aspects. So we work very hand in hand with our ES&T Directorate, and then comes National Homeland Security and Technology, where we study critical infrastructure needs and how does this all work together, looking at cyber concerns and more. This slide kind of talks about the development needs. I kind of have talked about it in our previous few slides. I'm going to skip that. And then I talked about this, looking at new materials brings up the need to make sure we have codes and standards. So there's an effort going on between US and Canada to support reactor design, regulators, and other stakeholders. And so this is, ARCS was established to support that need, which is mainly the organization involved with NEI and EPRI. And there's a report for more details if somebody's interested. Because when you do these things, you got to make sure you have codes and standards available to qualify those materials. Again, codes and standards, performance integrated materials use high temperature environments, qualifying and making sure that we have system in place to qualify those things, working closely with our international participants, WNA, IAEA, and other organizations. Looking at the time, I'm going to go pretty fast here. SMR development needs enable the future of nuclear energy through innovation. So looking at, as I talked about, Magnet, which provide us a test bed for experimental testing, gaining data, advanced reactors, design and deployment, looking at advanced technologies. And then further, we heard from a couple of panelists talk about digital engineering. Basically making sure that we use upcoming AI, ML technologies, digital engineering in place to support and learn from those things, because it'll be hard and impossible to run all the experiments. So can we do something, employ digital engineering and see how the system would behave? Then we have, as I talked about ATR, we have post-radiation examination capabilities, and then establishing test beds, both nuclear and experimental. Okay. A little more on test beds, and then also not just system as a whole, but how do they integrate with grid and other systems? And because each system brings a thermal inertia, so we need to understand how that behaves so we can do better modeling and learn from it. So again, as far as you can adopt and learn from each other and work in conjunction with university and industry, I think we'll make the SMR a reality. So with that, thank you all for listening. Thank you.
Thank you very much. So I would like to invite all the speakers to come on the stage now for the Q&A session. So the Q&A session is open now. You can raise your hand, ask questions, state your name, your country, your organization. We'll start one by one from the first presenter, Piyush, so you can ask one question to Piyush, and then we'll follow on according to that as well. So if audience has a question, please raise your hand and you can ask the question now. Okay, I see one hand raised. Please go ahead.
I'm Dan Șervănescu, RoPower SA, Romania. I want to make a comment and to ask a question. We have various papers published related to the fact that nuclear power plant is not one technology, is an envelope of technologies. The governing one is the technology of the core. However, it's not the only one technology. All the technologies have their own time life and their own limitation in developing and being obsolete. So the interface between core technology and digital technology is representative for this interface. Some interfaces are friendly, some are not. So when we plan a nuclear power plant, we have to consider the fact that we are now designing in the period of Industry 4.0. There are a lot of technologies appearing, we have to consider them. Nanotechnologies for fabrication, technologies, quantum computing, many other things that will appear very soon. But one thing I wanted to underline and to ask the question is human technology. We are building a plant for the next 60 years. That means they will be designed, operated by generation alpha, beta, human technology. Do we consider them actually?
Thank you for the question. So certainly I totally agree. So I mean, system is changing, things are evolving, and as I said, that's why the experimentation, demonstration becomes very important. But at the same time, while we do all that aspects, having human interface is very, very essential. Okay, so that's why we have a group which looks at that. Along with when you adapt new technologies, there would be some challenges that come up. So basically to address those things, you can't just rely on AI, ML, right? You gotta have human intervention where needed to understand the problem, the solution. As I said, you can have infinite solutions, but you gotta have the right expertise to make sure the solution is right to the problem that you're solving. So nothing can really replace experience. The advancements I talked about digital engineering and other things are still the tools. At the end of the day, it's up to the user how you use the tool in an efficient manner. So I'll leave it at that and see if my colleagues want to add.
Anybody else wants to add something? Nuri? Okay.
Me?
Yeah, please go ahead. If you want.
Okay, thank you. In my point of view, the key point is the collaboration. So many technology, many tools, many generation, and we need to collaborate all the tools. In my case, for example, we use several software to analyze one case. For one cases with different software will have result slightly different maybe. But when we complete one another difference, we will have the new collaboration and a good result. That's for me. Thank you.
Thank you very much. So next we're going to take questions for Paul. So we're going to go one by one with the speakers. So if you have any questions for Paul, who presented on Hexana, please raise your hand. Okay, please go ahead.
Okay, my name is Fitria from Indonesia. I'm interested in high temperature storage device in Hexana. Is it possible to apply this system to HTGR? Okay, thank you.
Yes, I think that several projects around the world use its thermal storage. It's a benefit of the high temperature of Gen 4 reactor. So you have for HTGR, I think the USNC design in the US and Canada that have one of the projects with thermal storage. Maybe for molten salt reactor, you have the Moltex Flex company that use also thermal storage. So it's benefits of the high temperature. At CEA, before I was at Hexana, we test this kind of heat storage system also with SMR, water SMR, Gen 3 water SMR. But due to the lower temperature, 300 degrees, the heat storage system is very, very, very big in terms of heat exchange between the reactor and the heat storage. So it's not very a benefit out of classical SMR. It's really a feature of high temperature Gen 4 system, but it could be applied with sodium, lead fast reactor also, and HTGR, obviously. Yes.
Great. Thank you. I have just one quick question also, Paul, if you can comment on. I know you're the CTO, so you have to cover many stuff. But specifically, can you comment a little bit on the fuel availability for MOX? Have you looked at what's the status for the availability for fuel for MOX that you'll require? And are you also looking at pre-processing MOX in the first phase or not?
Yes, the goal of Hexana is to use a MOX fuel. So MOX is a mixed oxide fuel between uranium and plutonium from used fuel from PWR. So basically, this fuel is well known in France because we operate Phoenix and Super Phoenix with this fuel. We fabricate this fuel. We retreat this fuel in a lag plant. The point is because we close our sodium fast reactor plant, we also close the facility to fabricate and retreat this kind of MOX fuel. But the knowledge and the know-how for this industry is present in France. So our challenge with our partner, mainly Orano, is to have a pilot facility to be built in 10 years to start our first reactors in 2035 with a full batch of MOX fuel. Because the real power of sodium fast reactor is to be fueled by MOX, I think.
Thank you. Thank you very much, Paul. We have 5 more minutes in the session, but we want to give chance to each speaker and everybody to ask questions to them. So next question, has somebody question for Guido as well? If not, then I have a question for you as well. In your test 100C, I'm assuming that was for the natural circulation test as well? The test 100C was for natural circulation?
Yes.
And I saw that in one of your curves, the mass flow rate was completely off. Do you have like some specific reasons for that? Were you able to observe why was that case? And
sorry, what was
the mass flow rate was completely off from the prediction? And could this be because of you used only relap 5? Do you think there is some other code that could better predict? Or was it because it's too complicated in general?
As I mentioned, I was not directly involved in this project, but as far as I know, in the Elsewhere project, we thought about just using relap 5 at the beginning, and also because of the expertise of Italian companies with this code. And honestly, I don't have an explanation about the reason why the mass rate went to 0.
Yeah, sure, please.
So I mean, again, working in heat exchangers, and I've done both design and testing, so just would like to comment a couple of things. You know, it tends to happen that irrespective of it's relap or something, you never find one tool that can solve all the problems. So as an experimentalist, I always encourage folks to look at your conservation equations, all those things to understand what's in it. Sometimes, especially in heat exchanger thing, when you talk about it, you got to look at the Nusselt number thing because this is a compact heat exchanger, so you know, the geometry inside would play a big impact. And normally that's not known. It's not a conventional shell and tube that you can use similar. So there are a lot of discrepancies that come, you know. So in those compact, if you don't know what's inside inside how the structure is laid out, there would be, the pressure drop might be off than conventional, so, you know, which might lead to uncertainty.
Okay, great. Thank you, Piyush, for the comment. So we'll move, okay. Please go ahead, yeah.
Hello, I'm Guang Hu from Technical University Eindhoven, the Netherlands. I want to ask a question for Professor Piero. Thanks for your detailed presentation just now. Maybe my question is a little bit challenging. Hopefully it will be not annoying. So I want to ask from your personal perspective, which one kind or two kinds of SMR would be most promising in future regarding the commercial availability and the public acceptance?
Thank you. No, I think if you look at large reactors, definitely pressurized water reactors. It's proven technology and very significant experience in many countries. Definitely, I hope that Russia will put into operation their Brest 300 OD, if it will be breeding reactor. But I don't think that many countries can do that. I am sure that China, Russia, United States, UK, France can do that, but countries who has no such long history of these things and not so much money to do that, I think it will be quite tricky. Even sodium fast reactors is very tricky. Due to this, definitely pressurized water reactors, it will be number one for many countries.
Yeah, I think picking favorites is always challenging. Please, next.
I've got a question for Mr. Igor. I mean, it was an excellent presentation what you gave in, and from there I understand that there are only two countries, which is Russia and China, who have moved into building an SMR and operating them. Is there any data available from them? What are the challenges? How much it cost? What sort of benefits, or what were the failures, or what were the advantages? I think since a lot of speakers spoke that we need to have inter-country, interstate libraries and universities, going together and finding solutions to these things. So I think we have two countries which are forerunners in these technology. So is there some sort of a data which has been available to understand what were the challenges they had, and what are the advantages of following the similar kind of technologies by the other manufacturers? Thank you.
Thank you. No, but first of all, usually such things not published. You can get some information, just some sort of internally. What I know that KLT-40S was installed on two icebreakers in 1989 and 1990, but KLT-40S as floating nuclear power plant appeared in 2019. Eventually, 29 years took to move from propulsion reactors to regular one. What I know, it's we have this handbook from IAEA. Russians added 3 or 4 passive safety systems to the propulsion reactor. It's not like you will take anything what is known from submarines or from aircraft carriers, reactors, and put in civil engineering. It's also some extra challenges. And I think that due to quite a small space, they have not implemented secondary steam reheat. KLT-40S is actually only 26% thermal efficiency. What I think about the helium-cooled reactor, I know from my previous things that helium has the smallest molecule. Definitely it can be problems losing helium during cooperation. Of course, originally also was some ideas that you might have graphite dust from the pebbles. Yes, it also can be a problem. Due to these things we can expect. And of course, my understanding that we definitely need to wait maybe 3-5 years when we can really confirm by China that this reactor is proven, operating, and all problems solved. Because my personal opinion that it's not good idea to sell reactors which are not proven. Test in your country, 3-5 years, major problems definitely will be there. Of course, later on can be materials problems, but it will be later on. But major one definitely should be fixed.
Great. Thank you, Igor. So we need to wrap up. So if there is one last question for Nuri before I ask Ms. Iyengar to wrap up the session, we can take one last question for her, and then I'm going to ask Ms. Iyengar to wrap up the session. Anybody else has a question for Nuri? Okay, then please.
I just want to say thank you to all of our presenters for this session. I think we had some really interesting talks on global perspectives, global trends, also getting into specific test and evaluation, modeling simulation from Indonesia, Italy, and industry perspectives from France, and also a lot of robust work going on at Idaho National Lab to support U.S. nuclear industry through some really robust test beds. So thank you again, really, for this robust session. Welcome everyone to stop by the Industry Night event at 5:45. Thank you.
she left me with a broken heart. She fooled me twice and it's all my fault. She got too deep, now she left me scored. Now there's so many thoughts going through my brain. Now I'm taking these shots like it's Novocaine. Ooh, I fall apart down to my core. Ooh, I fall apart down to my core. Didn't know it before. Surprised when you cut me off guard. Only some truly I bought. You was my shorty I thought. Never got a feeling this hard. Harder than the liquor I pour. Tell me you don't want me no more, but I can't let go. Everybody told me so. Feeling like I sold my soul. Devil in a form of a whore. Devil in a form of a whore. You said it. Now you said it. You said it. We'll be together. I fall apart. I fall apart. Eyes keep pouring and the dream keep flowing. Try to brush it off, but it keep on going. Covered scars and I can't help showing. Weeping in the forehead and the tears keep blowing. Eyes keep